Look up at the night sky, past the familiar glow of the moon and the scattered stars, and let your gaze travel into the profound, velvet blackness that stretches for billions of light years. In that moment of quiet wonder, a single, timeless question almost certainly forms in your mind: are we alone? For all of human history, this has been the ultimate mystery, a question whispered by philosophers and dreamed of by scientists. But what was once pure speculation is now transforming into one of the most thrilling scientific endeavors of our time. We are no longer just asking the question, we are actively hunting for the answer, assembling clues from across the cosmos with tools and technologies that would have seemed like magic just a generation ago. We are living in the golden age of cosmic discovery, a moment where the line between science fiction and science fact is blurring before our very eyes. This isn't just about finding little green men, it's about uncovering the fundamental principles of life itself and our place in this vast, astonishing universe. Imagine for a moment that you are a detective, but instead of a magnifying glass and a trench coat, your tools are space telescopes that can analyze the atmospheres of distant worlds, rovers that can taste the soil of alien planets, and radio antennas listening for a whisper in the cosmic noise. The case file is the entire galaxy, and the clues are pouring in at an unprecedented rate. Every few months, it seems, a new headline breaks about a potentially habitable world, a mysterious signal, or a chemical signature that should not exist without a biological explanation. These aren't just incremental steps, they are monumental leaps that are fundamentally reshaping what we thought was possible. The collective evidence is building into something undeniable, a cascade of data pointing toward a reality that is both humbling and exhilarating. We are closer than ever to knowing that life exists beyond the blue marble we call home. This video is your invitation to join that investigation. We are about to embark on a journey through 30 of the most groundbreaking, head-spinning, and frankly, unbelievable discoveries that have scientists around the globe saying we are on the verge of a paradigm shift. We will explore distant ocean worlds hiding beneath miles of ice, decode the complex chemistry of exoplanet atmospheres, and delve into the strange, resilient life forms right here on Earth that are rewriting the rules for where life can thrive. This is a cosmic detective story, and each piece of evidence brings us one step closer to solving the greatest mystery of all. So get comfortable and let's dive into the clues that are making us rethink our solitary existence in the cosmos. Our investigation begins not in the distant reaches of the galaxy, but right next door with our closest planetary neighbor, Venus. For decades, Venus has been dismissed in the search for life, a textbook example of a runaway greenhouse effect. Its surface is a crushing, scorching hellscape, hot enough to melt lead, with pressures that would instantly flatten any earthly machinery. It was the last place anyone expected to find a potential signature of biology. That's why the announcement in September of 2020 sent shockwaves through the scientific community. A team of astronomers had detected the spectral signature of phosphine gas in the temperate upper cloud decks of Venus. Now on Earth, phosphine is a molecule that is notoriously difficult to produce through ordinary geological or chemical processes. Here, it is almost exclusively associated with anaerobic life microbes that thrive in environments without oxygen like swamps, or crucially, it is manufactured industrially. Finding it in the clouds of Venus was like smelling a whiff of industrial smoke in the middle of a pristine, untouched wilderness. It was a signal that something unusual, something that shouldn't be there, was happening. The immediate and furious debate that followed this discovery highlights just how carefully scientists approach these extraordinary claims. The initial reaction was a mixture of excitement and deep skepticism. Other research teams scrambled to reanalyze the data, questioning the methods used to identify the phosphine signal. Could it be an instrumental error, Was there some unknown, exotic volcanic or atmospheric chemistry on Venus that we simply don't understand, a non-biological process that could churn out this gas? This rigorous back and forth is not a sign of failure. It is the very engine of science testing and probing a potentially revolutionary finding. The Venusian phosphine debate forced a fundamental re-examination of the planet itself. If the gas is truly there and is not biological, then we have a huge gap in our understanding of Venusian geology and chemistry. But if it is biological, well, that opens a door to a possibility so thrilling it redefines our concept of habitable zones. This leads us to the compelling hypothesis of airborne life. While the surface of Venus is utterly inhospitable, about 30 to 40 miles up, the environment is surprisingly Earth-like. The temperature and pressure in that specific cloud layer are not so different from conditions in our own lower atmosphere. It's still a hostile place with clouds made of sulfuric acid, but we know that extremophile microbes on Earth can survive in incredibly acidic environments. The idea is that microbial life could potentially exist there, not on the surface but floating, dwelling within the water droplets of the clouds, forming a persistent aerial biosphere. These would not be complex creatures but tiny, hardy microorganisms, a constant haze of life drifting in the Venusian skies. To settle this debate once and for all, we are sending new eyes to our sister planet. Missions like NASA, DAVINCI+ are specifically designed to plunge through the Venusian atmosphere, sampling its composition with exquisite precision as it descends. It will be able to directly measure the chemistry of those mysterious cloud layers and finally determine if the phosphine is a ghost in the machine or the first tangible evidence that we have been sharing our solar system with life all along. While Venus presented us with a tantalizing atmospheric mystery, our next discovery takes us to a frigid, icy moon orbiting the gas giant Saturn, a world that has fundamentally rewritten the textbook on where life could potentially thrive. The Cassini spacecraft, which spent over a decade studying the Saturnian system, made one of its most profound observations not by landing, but by flying directly through the glittering, magnificent plumes erupting from the south pole of Enceladus. Imagine a world smaller than the British Isles with a surface of pristine, almost pure water ice that reflects sunlight like a brilliant cosmic jewel. Yet beneath this frozen, tranquil crust lies a global ocean of liquid water, and this hidden sea is forcefully venting its contents into space through massive geysers that shoot hundreds of miles into the vacuum. Cassini didn't just photograph these plumes, it dove right through them, using its onboard instruments to taste and analyze their composition as it sailed past. What it found was nothing short of revolutionary. The analysis revealed that these plumes were not just simple jets of water vapor. They were a complex cocktail, a rich soup of chemicals that sent astrobiologists into a frenzy. Cassini detected significant concentrations of salts, similar to those found in Earth's oceans, and silica nanoparticles, which strongly suggest that hot water is interacting with a rocky core on the ocean floor. But the most electrifying find was the unambiguous signature of complex organic molecules. We're not talking about simple carbon compounds. These were large, heavy molecules with molecular masses well over 200 atomic units, the kind of intricate carbon-rich structures that form the essential building blocks of life as we know it. Think of amino acids and the nucleotide bases that make up our DNA. Finding these on Enceladus is like discovering a fully stocked kitchen on a deserted island. All the ingredients are present and waiting for the right recipe to come together. This transforms Enceladus from a curious icy moon into one of the most compelling targets in our entire solar system in the search for life. The classic recipe for a habitable world requires three key ingredients: liquid water, a source of energy, and the right chemistry. Enceladus checks every single box with astonishing confidence. we have the global subsurface ocean, a vast body of liquid water that may contain more volume than all of Earth's oceans combined. We have the chemistry proven by the complex organics and salts Cassini sampled. And critically, we have the energy. Enceladus isn't warmed by the distant sun. Its heat comes from within, generated by the immense gravitational tug of war between Saturn and its other moons. This gravitational flexing, known as tidal heating, keeps the interior of Enceladus warm and active, likely creating hydrothermal vents on the seafloor where hot, mineral-rich water gushes into the cold ocean. On Earth, such hydrothermal vents are teeming with life, entire ecosystems that thrive in total darkness, powered not by sunlight but by chemical energy. The parallel is impossible to ignore. The conditions on Enceladus seem to be a near-perfect mirror of the very environments where life may have gotten its start on our own planet. A future mission, perhaps one that can land near these plumes or even send a submersible probe through the ice, could be the one to finally answer the question of whether we are alone by finding life thriving in the eternal, dark warmth of an alien sea. Shifting our gaze from the icy plumes of Enceladus, we arrive at our third and perhaps most personal cosmic clue, unfolding right on the dusty surface of the planet that has captivated human imagination for centuries, Mars. For generations, we've projected our hopes and fears onto the red planet, wondering if we are looking at a barren wasteland or a world that once hosted, or perhaps even still hosts, a whisper of life. This long-standing question has found a modern focal point in a deceptively simple molecule, methane. The Curiosity rover, our robotic geologist tirelessly exploring Gale Crater, has been acting as a planetary detective, sniffing the thin Martian air for years. And what it has found is a pattern that is both baffling and incredibly exciting. The rover's onboard instrument, the tunable laser spectrometer, has consistently detected trace amounts of methane lingering in the atmosphere. This alone was a major discovery, but the real mystery lies in the behavior of this gas. The methane doesn't just sit there at a constant low level, it pulses. It experiences sharp, tenfold spikes in concentration that seem to come and go with the Martian seasons. It's as if the planet itself is breathing, exhaling small, mysterious puffs of gas and then falling silent again. To understand why this has scientists so captivated, we need to look at methane's story here on Earth. In our own atmosphere, methane is a powerful signpost of activity. While it can be produced by non-biological processes, like certain geological reactions involving water and rock, the vast majority of methane swirling around our planet is biologically sourced. It's a waste product from the digestive systems of cattle and termites, and it's released in massive quantities by methanogens, archean microorganisms that thrive in places devoid of oxygen, like deep underground, in the guts of animals or in watery wetlands. Finding methane on another world is like finding a single, lit match in a dark, empty room. It's not proof that someone is there, but it's a compelling indication that something just struck that match. The seasonal spikes on Mars are particularly tantalizing because they suggest an active, ongoing process. This isn't ancient methane trapped from a bygone era. This appears to be methane being produced and released in the present day. Is it possible that beneath the cold, radiation-scoured surface of Mars, in hidden aquifers or deep subterranean cracks, communities of Martian microbes are eking out an existence, their metabolic processes releasing these faint, seasonal signatures into the air above? Of course, the scientific community is rightfully cautious, and the hunt for non-biological explanations is just as vigorous. There are compelling geological theories that could account for the methane. A process called serpentinization, where certain types of iron-rich rocks react with water, can produce methane completely without the need for life. Another possibility is that the methane is ancient, trapped in underground clathrate ices that occasionally destabilize and release their stored gas in bursts. The sun's ultraviolet light also breaks down methane relatively quickly, which means any methane we detect must have been released quite recently, adding another layer of complexity to the puzzle. The central challenge is that our rovers, as incredible as they are, can detect the methane but cannot yet definitively determine its origin. It's like having a super-sensitive nose that can smell a pie baking from a mile away, but without being able to see the kitchen, you can't tell if it's a homemade apple pie or a store-bought cherry one. The ingredients might be similar, but the source is completely different. This profound uncertainty is precisely what fuels the next wave of Martian exploration. The quest to solve the methane mystery is a primary driver for missions like the European Space Agency's Trace Gas Orbiter, a spacecraft specifically designed to analyze the Martian atmosphere with far greater precision than any ground-based rover can. Intriguingly, the orbiter has often reported not finding methane in the global atmosphere at the same time Curiosity is detecting it locally on the surface. This discrepancy isn't a failure, it's a crucial clue in itself. It strongly suggests that the methane releases are not only seasonal but also highly localized. The gas seems to be seeping out from specific, confined areas and then dispersing quickly, meaning the rover might have driven right through a tiny, invisible plume of gas that the orbiter high above couldn't see. This paints a picture of Mars as a world with active, sporadic vents, places where something, be it geology or biology, is intermittently exhaling this enigmatic gas into the rusty air. Unmasking the true source of Martian methane is one of the most urgent goals in astrobiology, because if that source turns out to be biological, it would irrevocably change our understanding of life's tenacity, proving that even our seemingly dead neighbor holds a secret living heart. From the tangible chemistry of our solar system's worlds, we now turn our attention to the silent, invisible realm of radio waves and a single, startling event that has captivated and confounded scientists for nearly half a century. On a quiet Ohio night in August 1977, the Big Ear Radio Telescope, a massive stationary array operated by Ohio State University, was engaged in a routine sky survey, systematically scanning the cosmos for any signal that stood out from the natural background hum of the universe. The data was printed out line by line on wide sheets of paper, and a few days later, volunteer astronomer Jerry Amon was reviewing the long alphanumeric readout. His eyes scanned across rows of numbers and letters representing signal intensity, most of them unremarkable, until he saw a sequence so powerful and unexpected that he circled it in red pen and in the margin simply wrote, "Wow." That single, spontaneous exclamation gave the signal its immortal name, and it remains to this day the most compelling and enigmatic candidate for an artificial transmission from beyond our world. What made the WOW signal so extraordinary was its perfect, almost textbook profile. It was a strong, narrowband radio signal concentrated around the frequency of 1420 MHz. This is profoundly significant because that frequency lies within a protected, quiet band of the radio spectrum known as the hydrogen line, a region where the background noise of the universe is naturally minimal. It's a logical channel that any advanced civilization might choose to broadcast on, a sort of cosmic watering hole where everyone would know to listen. The signal blasted into the Big Ear's receiver for a full 72 seconds, the exact duration the telescope could focus on a single point in the sky as the Earth rotated, and then it vanished, never to be heard again. It had all the hallmarks of an intentional beacon. It was powerful, it was focused, and it appeared exactly as we would expect a message from the stars to appear. The fact that it was never repeated is the central core of the mystery, a one-time event that has taunted researchers with its fleeting, perfect nature. In the decades since, numerous attempts have been made to solve the puzzle. Astronomers have pointed far more sensitive radio telescopes, like the Very Large Array, back toward that same patch of sky in the constellation Sagittarius, listening for a repeat performance that has never come. More recently, a theory emerged that attempted to provide a natural explanation, suggesting the signal might have been a reflection from a passing comet. The idea was that the comet's cloud of hydrogen could have reflected a human-made transmission from Earth, creating a brief, powerful echo. This hypothesis was investigated with great interest, but it ultimately fell short. The specific comets proposed were not in the right part of the sky at that time, and the reflection mechanism didn't quite fit the signal's unique characteristics. This failure to find a natural source, while frustrating, only deepens the signal's intrigue. It has withstood every attempt at a conventional explanation, forcing us to confront the possibility that for those 72 seconds we were truly listening to something other. The enduring legacy of the WOW signal is not just about that one event. It's about the profound shift it created in our approach to searching the skies. It serves as a powerful lesson in the challenges of hunting for technosignatures, which are any detectable signs of technology, from radio transmissions to laser pulses or even massive engineering projects. The signal taught us that the cosmos might be full of transient, one-off events, brief windows of opportunity that close as quickly as they open. It highlighted the necessity of developing new listening strategies that can monitor vast areas of the sky continuously, rather than scanning one small point at a time. Modern projects like the Breakthrough Listen initiative are a direct response to this lesson, using powerful equipment to observe millions of stars and galactic centers simultaneously, hoping to catch the next WOW before it disappears forever. That single red-inked annotation on a piece of computer paper reminds us that the universe is capable of producing profound surprises, and it fuels the enduring hope that if we listen long enough and carefully enough, we might one day hear another signal, and this time we will be ready to answer. But what if the most promising places for life aren't Earth-like planets at all? Our next discovery pushes the boundaries of the habitable zone into truly alien territory, introducing a revolutionary class of exoplanets that scientists have dubbed Haitian worlds. The name itself is a portmanteau blending hydrogen and ocean, and it perfectly describes these incredible environments. Picture a planet significantly larger than Earth, up to 2.6 times its size, shrouded in a thick, dense atmosphere dominated by molecular hydrogen. Beneath this immense atmospheric blanket, the surface is not solid rock or continents, but a single, globe-spanning, liquid water ocean of unimaginable depth. These are not merely water worlds, they are supercharged aquatic planets where the conditions for life could be far more common and easier to detect than we ever imagined. The genius of the Haitian world concept is that it dramatically expands our search parameters. For years, the gold standard in the hunt for habitable planets has been the search for an Earth twin, a rocky world of a similar size, orbiting within its star's habitable zone, where temperatures are just right for liquid water to exist on the surface. But Haitian worlds shatter this narrow definition. Because of their massive, hydrogen-rich atmospheres which create a powerful greenhouse effect, these planets can maintain liquid water oceans even while orbiting much farther from their host stars. A planet that would be a frozen ice ball if it were Earth-sized could be a warm, watery Haitian world if it's larger and possesses that insulating hydrogen blanket. This means the traditional Goldilocks zone suddenly becomes much wider, encompassing many more stars and planetary systems where we previously thought life was impossible. Furthermore, their large size and expansive atmospheres make them ideal targets for our most powerful new tool, the James Webb Space Telescope. Analyzing the atmosphere of a small, rocky exoplanet is like trying to discern the color of a single candle flame from a mile away. Studying the atmosphere of a larger, puffy Haitian world, by comparison, is like analyzing the smoke from a massive bonfire. The signal is stronger, clearer, and packed with more information. This leads to the most exciting implication. Haitian worlds could be perfect hunting grounds for definitive biosignatures. The James Webb Space Telescope is uniquely equipped to probe the atmospheres of distant planets by analyzing the starlight that filters through them. In the chemical soup of a Haitian world's atmosphere, astronomers are specifically looking for pairs of gases that should not coexist for long without being replenished by something like life. On Earth, we have such a pair, oxygen and methane. These gases rapidly react with each other and destroy one another, so their persistent presence in our atmosphere is a clear sign that biological processes, photosynthesis and microbial metabolism, are constantly pumping them out. In the hydrogen-rich air of a Haitian world, scientists would search for a different but equally telling combination: dimethyl sulfide and methane. Dimethyl sulfide is a particularly compelling biosignature. Here on Earth, it is almost exclusively produced by marine phytoplankton, tiny organisms in our oceans. Finding this molecule in the atmosphere of a water-covered exoplanet would be incredibly strong, indirect evidence that a living oceanic biosphere exists below, potentially filling those alien seas with its own version of algae or plankton. The discovery of even a single Haitian world with this chemical fingerprint in its atmosphere would be a monumental step, suggesting that life may not only be common in the universe, but that it could flourish in environments we once considered utterly inhospitable. Moving from the vast, watery possibilities of Haitian worlds, we come to a creature so small it fits on the head of a pin. Yet its survival skills are so profound they reshape our entire concept of where life can endure. Meet the tardigrade, often called the water bear or moss piglet, a microscopic, eight-legged animal that is quite possibly the toughest life form we have ever discovered. These tiny, almost cute invertebrates are found in some of the most mundane places on Earth, from a patch of moss in your backyard to the sediment at the bottom of a lake. But their true nature is anything but ordinary. Tardigrades are masters of extreme survival, capable of withstanding conditions that would instantly kill almost any other known organism. They can be boiled, frozen to near absolute zero, crushed under immense pressures 6 times greater than that of the deepest ocean trench, and even be blasted with levels of radiation that would be fatal to a human in seconds. They achieve this through a state of suspended animation called cryptobiosis, where they curl into a little barrel-shaped tun, expel almost all of the water from their bodies, and dramatically slow their metabolism to an undetectable level. In this state, they are not truly alive in the active sense, but they are not dead either. They are in a state of profound pause, waiting for conditions to improve, sometimes for decades. This incredible hardiness was put to the ultimate test in a series of landmark space experiments. Scientists actually placed groups of tardigrades on the outside of a spacecraft and exposed them directly to the vacuum of space, a realm of zero pressure, freezing temperatures, and intense, unfiltered solar and cosmic radiation. For 10 days, these microscopic pioneers drifted in orbit, completely unprotected. When they were retrieved and rehydrated back on Earth, many of them not only revived but went on to reproduce perfectly healthy offspring. They had survived the full, brutal force of the space environment, something no other complex animal has ever done. This isn't just a fascinating biological curiosity, it's a paradigm-shifting discovery. It proves that complex multicellular life can, in fact, survive the rigors of interplanetary travel. This single experiment shatters a major barrier in a theory that was once considered pure science fiction, but is now taken seriously by scientists: the theory of panspermia. Panspermia is the compelling idea that life, or at least its fundamental building blocks, is not confined to a single planet. Instead, it could be a cosmic traveler, hitching rides between worlds on asteroids, comets, and cosmic dust. The concept has 2 main variations. There's panspermia, which suggests that resilient microorganisms could survive a journey through space while protected inside the interior of a rock, shielded from the worst radiation and heat. Then there's the more radical directed panspermia, the notion that an advanced civilization might intentionally seed lifeless worlds with microbial life. While that remains speculative, the tardigrade experiments provide powerful, tangible support for the basic premise of lithopanspermia. If a complex creature like a tardigrade can survive the vacuum and radiation of space, then it is entirely plausible that hardier, simpler organisms like certain types of bacteria or archaea could survive an even longer journey nestled safely within the crevices of a meteoroid. Now let's follow this idea on an epic journey. Imagine a scenario millions of years ago on an ancient wet Mars, a world we know had flowing water and a thicker atmosphere. Suppose microbial life had taken hold there, thriving in its lakes and rivers. Then a massive asteroid slams into the Martian surface. The impact is cataclysmic, but it doesn't necessarily sterilize everything. Chunks of Martian rock are blasted into space, and some of those rocks contain microscopic life, safely encased deep within, shielded from the heat of the ejection and the radiation of space. These rocks then become tiny, unguided spacecraft drifting for eons through the solar system. Eventually, by the sheer statistics of cosmic billiards, one of these Martian meteorites finds its way to Earth, plunging through our atmosphere and landing in a primordial ocean. The interior of the rock remains relatively cool, and the microbes within, having been in a dormant state similar to a tardigrade's ton, reawaken in a new, watery world. This is not just a thought experiment. We have physical evidence for parts of this chain. We have right here on Earth over 300 meteorites that we have identified as originating from Mars, confirmed by analyzing the tiny pockets of gas trapped inside them that perfectly match the Martian atmosphere. While we have not found definitive proof of living Martian microbes in them, we have found complex organic molecules. The pathway itself is proven. Rocks do travel from Mars to Earth. The only remaining question is whether any passengers ever made the trip alive. This radically alters our perspective on the origin of life and its distribution throughout the cosmos. If panspermia is a viable process, then life may not be a rare, miraculous spark that must ignite independently on each habitable world. Instead, it could be a single spark that, once lit, can spread like a cosmic wildfire carried by the natural debris of the universe. A single life-bearing planet in a young solar system could, through asteroid impacts, seed every other potentially habitable world in that system. This means that life on Earth might not be native at all. We could all be descendants of Martian immigrants, and the entire solar system could share a common, ancient family tree. Furthermore, this concept extends beyond our own star system. While interstellar travel is vastly more challenging, recent studies of objects like Oumuamua, the first known interstellar object to pass through our solar system, show that material from other star systems can indeed reach us. The building blocks of life, or even dormant life itself, could be crossing the immense gulfs between stars, turning the entire galaxy into a single, interconnected ecosystem. The humble tardigrade, by proving that life is far more robust and space-worthy than we ever dreamed, gives immense credibility to this awe-inspiring possibility, suggesting that we may not be isolated inhabitants of a single world, but rather citizens of an entire cosmos quietly teeming with related life. Now, let's journey 40 light-years away from Earth to a stellar neighborhood that has redefined our idea of a planetary system. Imagine a star not much larger than the planet Jupiter, a cool, red dwarf so faint you could barely see it with the naked eye from Earth. This is TRAPPIST-1, and for a small, quiet star, it has an astonishingly large and bustling family. Astronomers discovered that this single dwarf star is orbited by not one or two, but 7 rocky planets, each one remarkably close in size to our own world. The entire system is a study in cosmic compactness. You could fit the orbits of all 7 planets comfortably inside the distance Mercury orbits our Sun. This creates a breathtaking celestial dance. If you were standing on the surface of one of these worlds, the other planets would appear in your sky not as distant points of light, but as large, vivid moons, their geological features perhaps visible to the naked eye, creating a sky of unparalleled wonder. The most critical feature of this compact system is its habitable zone, that Goldilocks region where temperatures are just right for liquid water to exist. In most solar systems, we are lucky to find one, maybe two planets orbiting within this life-friendly band. But around TRAPPIST-1, the configuration is nothing short of miraculous. Of its 7 known Earth-sized worlds, a full 3 designated TRAPPIST-1e, F, and G are firmly situated within this temperate zone. This means that in a single stellar system, we have 3 primary candidates for hosting liquid water oceans on their surfaces. The implications are staggering. We are no longer searching for a single needle in a cosmic haystack. We have found a small cluster of needles all in one place. This system provides a unique natural laboratory, allowing us to study and compare the atmospheres of multiple potentially habitable worlds all at once, around the same star under similar but varying conditions. This tightly packed arrangement, however, comes with a significant asterisk in the form of the star itself. Red dwarfs like TRAPPIST-1 are notorious for their volatile youth. They are known to emit frequent and powerful stellar flares, eruptions of ultraviolet and X-ray radiation that could potentially strip away a planet's atmosphere over billions of years. A planet orbiting in the habitable zone of a red dwarf is also likely to be tidally locked, meaning one side permanently faces the star in eternal daylight, while the other is locked in perpetual frozen night. This could create extreme weather patterns, with howling winds circulating between the hot and cold hemispheres. The question, then, is whether any of the TRAPPIST-1 planets have managed to hold onto their atmospheres despite this stellar onslaught. An atmosphere is the key to life as we know it. It regulates temperature, provides pressure for liquid water, and hosts the complex chemistry that can create and sustain biology. Without a protective atmospheric blanket, even a planet in the perfect orbital position would be a barren, airless rock. This is precisely why the TRAPPIST-1 system has become one of the most urgent and exciting targets for the James Webb Space Telescope. Webb's powerful infrared eyes are perfectly suited to tackle the central mystery of these worlds. Do they have atmospheres, and if so, what are they made of? The method Webb uses is as elegant as it is effective. As each planet transits or passes in front of its host star from our perspective, a tiny fraction of the star's light filters through the planet's atmosphere. Different gases in that atmosphere absorb specific colors or wavelengths of this starlight. By analyzing the resulting spectrum, the chemical fingerprint of the missing light, Webb can identify the atmospheric gases present. The telescope is now actively hunting for biosignatures, the telltale chemical imbalances that hint at life. The most promising combination is oxygen and methane, 2 gases that rapidly destroy each other unless they are being constantly replenished by biological processes. Finding this pair in the air of TRAPPIST-1e, F, or G would be the strongest indirect evidence for life we have ever obtained. But the scientific promise of this system goes far beyond a simple yes or no answer. Because we have multiple worlds to compare, Webb's observations can provide a comparative planetary study that is simply impossible anywhere else. Imagine Webb analyzes the atmosphere of the innermost habitable zone planet, TRAPPIST-1e, and finds it to be a thick, Venus-like hellscape of carbon dioxide, its atmosphere stripped away by the star's early fury. Then it turns its gaze to the next planet out, TRAPPIST-1f, and detects clear signs of a robust, Earth-like atmosphere with water vapor and maybe even hints of oxygen. This comparative data would be a goldmine, telling us not just about the potential for life on one world, but about the resilience of atmospheres and the conditions that allow some planets to thrive while others fail. The TRAPPIST-1 system offers us a glimpse of an entire planetary ecosystem, a miniature solar system that could represent one of the most common architectural plans for life in the galaxy, given that red dwarfs make up the vast majority of stars in the Milky Way. The answers now being gathered by Webb could very well determine whether we live in a universe where life is a rare fluke or a cosmic commonplace. The search for life is no longer confined to our own solar backyard. It has expanded into the galaxy at large, powered by an instrument that feels like it was pulled straight from the pages of science fiction. The James Webb Space Telescope represents a quantum leap in our cosmic observational power, a tool so sensitive it can perform a chemical analysis on the atmosphere of a world orbiting a star dozens of light years away. It accomplishes this feat not by taking a direct picture of the planet, which is often lost in the blinding glare of its host star, but by watching with exquisite patience as the planet transits or crosses in front of that star from our point of view. During this celestial alignment, a tiny, almost infinitesimal fraction of the star's light filters through the planet's thin atmospheric veil. It's within this sliver of light that the secrets are held. Different gases in the atmosphere absorb very specific wavelengths of this starlight, and by carefully dissecting the resulting spectrum, the unique chemical barcode of the missing light, scientists can identify which gases are present, turning the telescope into a remote cosmic chemist. The true power of this method lies in the search for biosignatures, which are not merely the presence of a single gas, but specific combinations of gases that exist in a state of chemical imbalance, an instability that suggests something is actively replenishing them. Think of a seesaw with children constantly jumping on both ends to keep it in motion. Left alone, it would settle into stillness. In an atmosphere, the most compelling biosignature pair is molecular oxygen and methane. These two gases are highly reactive. They naturally destroy each other when they come into contact. On a sterile, lifeless world, you would not expect to find significant amounts of both existing together for long geological timescales. Their persistent coexistence is a powerful indicator of continuous production. On Earth, our abundant oxygen is almost entirely a product of photosynthesis from plants and microbes, while a large portion of our methane is produced by biological sources like methanogenic archaea and other life forms. Finding this same defiant duo in the air of a distant world would be the strongest indirect evidence for life we could possibly obtain with current technology. The James Webb Space Telescope has already begun delivering breathtaking data on specific, promising targets. One of its early highlights was the analysis of K2-18b, a mini-Neptune or potentially a Hycean world orbiting within the habitable zone of its star. When Webb studied its atmosphere, the data revealed a clear and robust signature of carbon dioxide and methane, but crucially, it found no evidence of ammonia. This particular chemical cocktail is highly suggestive of a water ocean beneath a hydrogen-rich atmosphere, exactly the kind of environment a Hycean world would possess. Even more tantalizing was a potential, though yet to be confirmed, signature of dimethyl sulfide. As we discussed, on Earth, DMS is only produced by life, specifically by marine phytoplankton. While this detection requires further validation, its mere possibility highlights how Webb is already skirting the edges of a monumental discovery, sniffing the air of an alien world for molecules that, as far as we know, can only be made by living processes. Another landmark target is the rocky exoplanet TRAPPIST-1e, part of that incredible 7-planet system. This world is almost exactly Earth's size and mass and resides squarely in its star's habitable zone. Webb has now observed multiple transits of this planet, and the initial atmospheric data is both profound and telling. The early results suggest that TRAPPIST-1e does not possess a thick, puffy atmosphere dominated by hydrogen. This immediately rules out it being a mini-Neptune and confirms its rocky nature. However, the data also shows no signs of a substantial atmosphere like our own, at least not one that is rich in carbon dioxide or other easily detectable gases. This could mean one of two things, each with dramatic implications. It's possible that the planet has a thin, Earth-like atmosphere that is simply harder to detect, perhaps dominated by nitrogen and oxygen. Alternatively, and perhaps more likely given the violent flares from its red dwarf sun, the planet may have had its atmosphere stripped away entirely, leaving it a barren, airless rock. This isn't a disappointment, it's a crucial piece of the puzzle. By comparing TRAPPIST-1e to its siblings, F and G, Webb is conducting a controlled experiment on planetary evolution, showing us in real time which worlds in a system can hold onto their life-sustaining blankets and which cannot. This new era of atmospheric spectroscopy is transforming the search for life from a theoretical exercise into a rigorous, data-driven hunt. Every observation, whether it reveals a bustling chemical network or an eerie silence, teaches us something vital. A non-detection of biosignatures on a promising world like TRAPPIST-1e forces us to refine our models of planetary habitability, particularly around the galaxy's most common stars. A potential detection of a molecule like dimethyl sulfide on a world like K2-18b forces us to confront the possibility that we have already found the first evidence of a biological process beyond our Earth. The James Webb Space Telescope is our generation's great explorer, a silent sentinel at the Lagrange point whose observations are systematically building a new chapter in human knowledge, one atmospheric spectrum at a time. But if the tardigrade shows us the vehicle for panspermia, the next discovery reveals the cargo. We now turn our attention to the most ancient rocks in our solar system, celestial time capsules that have been falling to Earth for millennia, meteorites. Specifically, a special class known as carbonaceous chondrites. These are not just any space rocks, they are primordial relics, leftover building materials from the very formation of our solar system over 4.5 billion years ago. They have remained largely unchanged since then, frozen in time, and when we crack them open, we find something astonishing. They are not barren. They are rich in organic chemistry, containing a veritable soup of the very compounds that are essential for life as we know it. The most famous of these is the Murchison meteorite, which fell in Australia in 1969. This event was a gift to science as the pristine fragments were collected quickly, minimizing contamination from Earth's own biology. When scientists analyzed the Murchison meteorite, they were stunned. It was loaded with a diverse array of complex organic molecules. Most significantly, it contained over 90 different amino acids. Amino acids are the fundamental building blocks of proteins, which are the workhorse molecules of all known life forms. What's truly breathtaking is that while life on Earth uses about 20 standard amino acids to build every protein in every organism, the Murchison meteorite contained many of those 20, plus dozens more that aren't commonly used in terrestrial biology. This tells us something profound. The universe appears to have a bias, a natural tendency to cook up these life-essential molecules. They aren't rare or special to Earth. They are a default product of cosmic chemistry, forming in the dark, cold molecular clouds of space and then getting incorporated into asteroids and comets as solar systems are born. This discovery powerfully bolsters the idea of panspermia, not by proving life traveled, but by proving its raw ingredients are universal and can be delivered. Think of the early Earth around 4 billion years ago. It was a violent, molten world constantly bombarded by asteroids and comets. This period, known as the Late Heavy Bombardment, was once thought to have sterilized the planet. But we now see it in a different light. It's possible that this cosmic pummeling wasn't a curse but a blessing. Each impact from a carbonaceous chondrite meteorite was like a supply ship from the cosmos, crashing into the young oceans and dumping its payload of amino acids, sugars, and nucleobases, the very letters of the genetic alphabet, into the primordial soup. This wouldn't have been a one-time event, but a constant rain of organic material, significantly enriching the probiotic chemistry of early Earth. The question shifts from how did life start from nothing? 2. How did these universally available ingredients delivered in abundance finally assemble themselves into the first living cell? The evidence doesn't stop at amino acids. Further analysis of meteorites like Murchison has revealed an even more complex chemical landscape. Scientists have found fatty acids which can form the membranes of cells, and nucleobases like uracil and xanthine, which are key components of RNA and DNA. They've even detected the presence of sugars, another critical piece of the biological puzzle. What's remarkable is that some of these organic compounds in meteorites show an excess of one molecular handedness or chirality. Many organic molecules come in two versions that are mirror images of each other, like a left and a right hand. Life on Earth is homochiral. It exclusively uses right-handed sugars and left-handed amino acids. The fact that some meteorites show a slight bias toward the same chirality used by life is a tantalizing hint that the cosmic chemistry that predates life might already be nudging things in the right direction. These meteorites are not just carrying random chemicals, they are carrying a pre-selected toolkit, a starter set that seems almost purpose-built for the emergence of biology. This transforms our perspective on the origin of life. If the basic building blocks are common throughout the solar system and can survive the journey through space, and we know they can because we're holding them in our hands, then the probability of life arising on any wet, rocky world goes up dramatically. It means that the spark of life may not need to ignite from absolute scratch on every single planet. Instead, the universe does the hard work of prebiotic chemistry in the vast interstellar clouds and the asteroid belts. All a planet needs to do is provide a stable, watery environment for those delivered ingredients to mix, interact, and eventually cross the threshold into a living system. The panspermia hypothesis, once a fringe idea, is now supported by a solid chain of evidence. We have the vehicle, proven by the tardigrade's resilience. We have the cargo, proven by the Murchison meteorite's rich organic inventory. And we have the delivery mechanism, proven by the countless impact craters on every rocky body in our solar system. It suggests that life could be a cosmic imperative, and that we, and every other living thing we might one day discover, may all be descendants of the same ancient interstellar recipe. From the ancient organic cargo carried by meteorites, we turn our attention to a more contemporary and equally stunning revelation. One that suggests the ingredients for life may not just be a memory from the past, but a present-day reality on the planet next door. Beneath the stark, frozen desert of the Martian South Pole, hidden under nearly a mile of solid ice, scientists have uncovered evidence of a vast liquid water reservoir. This discovery didn't come from a rover's drill or a lander's scoop, but from a sophisticated radar instrument aboard the European Space Agency's Mars Express orbiter, which has been circling the red planet for nearly 2 decades. The instrument, known as MARSIS, works by sending low-frequency radio pulses down to the Martian surface. These pulses penetrate the ground, and when they hit a boundary between different materials like ice and liquid water, a portion of the signal reflects back to the orbiter. By meticulously analyzing these returning echoes, scientists can create a subsurface profile, essentially giving the planet a sonogram. What they saw in the data from a region called Ultimi Scopuli was a brilliant, sharply defined reflection, an anomaly that was far brighter than the echoes from the surrounding rock and ice. The shape and intensity of this signal were a perfect match for what you would expect from a large body of liquid water. The conclusion was as stunning as it was simple. They had found a subsurface lake roughly 12 miles across, buried deep beneath the ice cap. The existence of liquid water so close to the surface in such a frigid environment seems counterintuitive at first. The average surface temperature at the Martian poles is a brutally cold -190 degrees Fahrenheit, far below the freezing point of pure water. The secret to this lake's liquid state lies in a combination of pressure and chemistry. The immense weight of the overlying ice cap creates tremendous pressure on the water below, significantly depressing its freezing point. More importantly, the water is almost certainly not pure. It is a brine, a thick, salty soup saturated with perchlorates and other salts known to exist in the Martian soil. These salts act as a powerful antifreeze, allowing the water to remain in a liquid state even at temperatures as low as -90 degrees Fahrenheit. This creates an environment that, while far from hospitable by our standards, represents a profound shift in our understanding of modern Mars. For decades, the search for liquid water on Mars focused on ancient riverbeds and dried-up lake bottoms, relics of a warmer, wetter past. This discovery, however, points to a potentially active contemporary water cycle, suggesting that liquid water could be a permanent, though hidden, feature of the Martian world today. The immediate and obvious question is whether such a harsh, dark, and salty environment could possibly support life. The water in these subglacial lakes is likely extremely cold and hypersaline, several times saltier than Earth's oceans. This presents a dual challenge for any potential organism. The high salt concentration creates an osmotic pressure that can literally suck the water out of a cell, causing it to desiccate and die. Furthermore, the perpetual darkness means no sunlight is available to power photosynthesis, the foundation of most food webs on Earth. Yet, even with these severe constraints, we cannot dismiss the possibility of life. Here on our own planet, we have found entire ecosystems thriving in seemingly impossible places that serve as powerful analogues. Deep beneath the Antarctic ice sheet, in the pitch-black, frigid waters of subglacial Lake Vostok, scientists have discovered microbial life surviving in isolation for millions of years. These organisms are chemolithioautotrophs, a mouthful of a name for life forms that derive their energy not from the sun, but from chemical reactions between rocks and water. They feed on the minerals in the bedrock and dissolved gases, forming a complete food chain that operates entirely independently of sunlight. The parallels between Lake Vostok and the Martian subsurface lake are impossible to ignore. If life can persist in the cold, dark, and nutrient-poor environment under the Antarctic ice, then the fundamental principles of biology tell us that similar life could, in theory, exist in the analogous environment on Mars. The microbes would need to be extreme halophiles, organisms adapted to love high salt conditions, and they would need a metabolism capable of extracting energy from the Martian rocks and salts, perhaps by reducing perchlorates or oxidizing iron and sulfur compounds. The discovery of such a habitat fundamentally redefines the modern-day astrobiological potential of Mars. It means we are no longer solely searching for fossils of ancient life preserved in dried-up riverbeds. We are now contemplating the existence of a potential, still-living subsurface biosphere, a refuge where life could have retreated as the Martian surface became increasingly cold and arid over billions of years. These deep aquifers could form a connected network, a kind of subterranean archipelago of habitable zones, where microbial communities have persisted in isolation, evolving along their own unique path for eons. Finding even a single, dormant microbial cell in that buried Martian lake would be one of the most profound discoveries in human history, proving that life is not a unique property of Earth, but a phenomenon that can take root on multiple worlds. This single radar echo has transformed our view of Mars from a dead planet to a world that may still hold its most precious secrets locked away in the dark, silent waters beneath the ice. While we often search for life in the atmospheres of distant worlds or the subsurface oceans of alien moons, our next discovery serves as a powerful reminder that evidence could literally be passing through our own cosmic neighborhood. In October 2017, astronomers at the University of Hawaii made an unprecedented detection using the Pan-STARRS telescope. They spotted a faint, fast-moving object that, upon calculating its trajectory, was revealed to have come from far beyond our solar system. This was not a comet or asteroid from our own backyard. It was a visitor from the deep space between the stars, named Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was a truly historic find, the first known interstellar object ever observed within our planetary system. What made Oumuamua so immediately fascinating beyond its origin was its utterly bizarre physical characteristics. As it tumbled through our solar system, astronomers tracked its brightness, noticing that it varied dramatically by a factor of 10 every few hours. The only logical explanation for such an extreme fluctuation was an object with a highly unusual shape. Oumuamua wasn't a roughly spherical rock. The data indicated it was profoundly elongated, shaped like a pancake or a cigar, with an estimated length up to 10 times greater than its width. Nothing like this exists in our own solar system in such an extreme form. Then came the second major puzzle, its motion. As Oumuamua sped away from the Sun, it exhibited a slight but definite non-gravitational acceleration. In simple terms, it was moving just a tiny bit faster than could be explained by the gravitational pull of the Sun and planets alone. This is a common phenomenon for comets, as the Sun's heat vaporizes their icy surfaces, creating jets of gas that act like a natural rocket engine. Yet, when every telescope pointed at Oumuamua, they saw no coma, no cloud of gas and dust, no tail whatsoever. It was dark with a surface that appeared more rocky or metallic than icy, and it was accelerating without any visible sign of the outgassing that should have caused it. This combination of mysteries, the strange shape and the hidden force acceleration, naturally sparked a wide spectrum of theories. The most conservative explanations proposed that it could be a fractal-like aggregate of dust, a sort of cosmic dust bunny, or a shard from a planetary collision that was tumbling in a way that mimicked an elongated shape. The most provocative theory, put forward by Harvard astronomer Avi Loeb, suggested we consider an artificial origin. He proposed that Oumuamua's flat, thin shape and its acceleration could be explained if it were a light sail, a piece of advanced technology designed to be pushed by the radiation pressure from starlight. In this scenario, the object wouldn't need to vent gas. The gentle but constant pressure of photons from the Sun could provide the exact kind of push needed to account for its extra speed. This was not a claim of certainty, but a compelling argument that, given the object's unique properties, an artificial origin should remain on the table as a possibility. The scientific consensus, however, has largely settled on more natural, though still extraordinary, explanations. The leading hypothesis today is that Oumuamua was likely a very unusual type of comet, composed of a different kind of ice than we're used to. It might have been made predominantly of solid nitrogen, much like the surface of Pluto. As the Sun warmed this nitrogen ice, it wouldn't have created a dusty gas tail like a water ice comet. Instead, the nitrogen would have sublimated directly from solid to gas, creating pure, invisible jets that provided the thrust without the telltale dusty cloud. Its strange shape could then be explained as a result of its long journey through interstellar space, where cosmic rays and collisions gradually eroded it into that peculiar, flattened form. This nitrogen iceberg theory elegantly explains both the acceleration and the lack of a visible coma, fitting the data without requiring new physics or alien technology. Regardless of which explanation you find more compelling, the lasting legacy of Oumuamua is undeniable. It cracked open an entirely new field of astronomy, the study of interstellar objects. Its visit proved that our solar system is constantly being traversed by material from other star systems, material we simply lacked the technology to see until now. This revelation fundamentally changes the panspermia equation, suggesting that the building blocks of life, or even dormant life itself, could be hitching rides on these interstellar travelers, moving between planetary systems across the galaxy. Oumuamua's mystery, while perhaps solved by conventional means, has permanently expanded our imagination. It forces us to ask not just if life is out there, but if its artifacts or probes might one day drift silently through our domain, challenging us to be clever enough to recognize them. This single, enigmatic visitor has ensured that from now on, when we scan the skies, we are not just looking for signals or planets, but for the quiet, fast-moving shadows of travelers from other suns. Leaving behind the silent, icy mystery of the Martian subsurface, we voyage out to the realm of the gas giants, to a world so eerily familiar and yet so utterly alien that it feels like a distorted mirror of our own planet's past. This is Titan, the largest moon of Saturn, a place that has captivated scientists ever since the Voyager probes first pierced its hazy orange veil. Titan is the only moon in our solar system with a substantial atmosphere, a thick, soupy blanket of nitrogen and methane that is perpetually shrouded in complex organic smog. But the true marvel lies on its surface. When the Cassini spacecraft arrived at Saturn and released the Huygens probe on its historic descent, it revealed a landscape that was both breathtaking and bizarre. Titan has rivers, it has lakes and seas, it has shorelines, dunes, and even rain. But this is not a water cycle, with surface temperatures plunging to -290 degrees Fahrenheit. Water is frozen solid, harder than granite. Instead, Titan's hydrologic cycle is powered by liquid methane and ethane. On this frigid world, these hydrocarbons play the role that water does on Earth, evaporating from vast seas, forming clouds in the sky, and falling as a slow, cold rain that carves river valleys and fills deep lakes. The Cassini-Huygens mission did far more than just map this alien geography. It performed a chemical analysis that sent shockwaves through the field of astrobiology. As Cassini repeatedly flew through the upper layers of Titan's atmosphere, its instruments sampled a chemical factory of staggering complexity. High in the haze, ultraviolet light from the sun and energetic particles from Saturn's magnetosphere bombard molecules of methane and nitrogen, breaking them apart. These molecular fragments are highly reactive, and they immediately begin linking together into ever larger and more complex structures. Cassini detected a veritable zoo of these organic molecules, including benzene, a ring-shaped building block for more intricate compounds. But the most significant discovery was the unambiguous identification of vast quantities of vinyl cyanide and other heavy, carbon-rich polymers. This is where the connection to life's origins becomes electrifying. On the early Earth, before life emerged, our planet's atmosphere and oceans are thought to have been a vast, natural laboratory where simple molecules assembled into the complex organic compounds necessary for biology, a period known as the prebiotic era. We can only simulate this process in labs, creating what we call a primordial soup. Titan, however, is not a simulation. It is a real-world, full-scale prebiotic laboratory operating in real time according to its own frozen rules. It is actively and continuously manufacturing the very types of molecules that on Earth were the essential precursors to life, the thick orange haze that envelops the moon. That is not just smog, it is a constant planet-wide drizzle of these complex organic compounds, snowing down onto the surface and accumulating in layers that could be hundreds of feet thick over billions of years. Imagine the shores of Titan's methane lakes not as barren wastelands, but as tar pits rich in this organic material, a potential staging ground for the next steps in chemical evolution. This leads to one of the most compelling hypotheses about Titan's potential for life, albeit a life that would be fundamentally different from our own. Given the extreme cold and the absence of liquid water, any life on Titan could not be based on water biochemistry. Instead, it might use liquid methane as its solvent. This is not as far-fetched as it sounds. We know that vinyl cyanide, which Cassini found in abundance, can form stable, hollow structures called azotosomes in liquid methane at Titan's temperatures. These azotosomes are analogous to the lipid membranes that form the protective walls of every living cell on Earth. This means that on Titan, the fundamental building blocks for cellular structures may not only exist but could be naturally and abundantly forming in its methane seas. While we have no evidence that this has actually led to life, the fact that the prerequisite chemistry is actively occurring is a discovery of monumental importance. It demonstrates that the pathways to life are not necessarily limited to the warm, watery environments we are familiar with. The universe might have multiple parallel recipes for creating the conditions of habitability. The legacy of Cassini Huygens is that it transformed Titan from a distant, hazy orb into one of the most promising targets for future exploration. A mission concept called Dragonfly has been selected by NASA to take the next bold step. Dragonfly is not a rover in the traditional sense. It is a dual quadcopter, a robotic drone designed to fly through Titan's thick atmosphere, which makes flight remarkably easy due to the low gravity and dense air. This flying machine will be able to travel dozens of miles between landings, sampling the organic-rich sand dunes and the floor of an impact crater where water ice and complex organics are thought to have once mixed in a liquid water lake, albeit temporarily. Dragonfly's mission is to perform on-the-ground chemistry, to literally taste the surface and search for evidence of those key probiotic molecules, and perhaps even for chemical signatures that indicate the processes that lead to life are more advanced than we currently understand. By exploring this frozen, hydrocarbon-soaked world, we are not just looking for life as we know it. We are peering back in time at the chemical processes that may have set the stage for our own existence, and simultaneously learning that the universe's toolkit for creating life might be far more diverse and inventive than we ever dreamed. While we search for chemical signatures and microscopic life, a much grander question looms. Could there be civilizations out there so advanced that their engineering projects are visible across interstellar space? This brings us to a fascinating framework for imagining such possibilities, known as the Kardashev scale. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this scale is a way of classifying a civilization's level of technological advancement based on its energy consumption. A Type I civilization is a planetary species, one that has learned to harness all of the energy available on its home world, including solar, geothermal, and oceanic power. Humanity isn't even there yet. We're currently sitting at about Type 0.73. A Type Roman III civilization is almost godlike, controlling the energy output of an entire galaxy. But it's the middle step, a Type Roman II civilization, that has become a major focus in our modern search for intelligent life. A Type Roman II civilization would have graduated from planetary to stellar engineering. It would be capable of capturing and utilizing the total energy output of its host star. To put that in perspective, such a civilization would command energy on a scale 1 trillion times greater than our current global consumption. They wouldn't just have solar panels on their roof, they would effectively have a solar panel surrounding their sun. How could any society possibly achieve such a feat? The most famous theoretical concept for this is the Dyson sphere, named after physicist Freeman Dyson, who popularized the idea. It's crucial to understand that this isn't usually imagined as a single, solid, rigid shell. That would be mechanically impossible with known materials. Instead, a more plausible design is a Dyson swarm, a vast collection of individual energy collecting satellites or space habitats, numbering in the billions or trillions, orbiting the star in a dense formation. This swarm would capture the star's light and convert it into usable energy, powering a civilization whose needs we can barely comprehend. The sheer scale of such a project is staggering, but from an engineering perspective, it's not forbidden by the laws of physics. A species that had mastered its own solar system would likely see this as the next logical step for growth and survival. This leads to one of the most brilliant aspects of the search for such civilizations: how to detect them. You wouldn't look for a radio signal or a laser pulse. You would look for the unintended consequence of all that energy harvesting. Think about it. If you surround a star with trillions of energy collectors, what happens to the starlight? The satellites would absorb the visible light to do their work, but energy cannot be created or destroyed, only changed in form. According to the laws of thermodynamics, all that absorbed energy would eventually be re-radiated back into space as waste heat, primarily in the form of lower energy infrared light. So, from a great distance, a star enshrouded by a Dyson swarm would present a very strange signature. It would appear unusually dim in the visible part of the spectrum, or it might even flicker erratically as the swarm rotates, but it would glow brilliantly in the infrared. It would, in essence, look like a star that is much cooler than it should be, radiating a disproportionate amount of infrared warmth for its size and type. Finding a star that looks like a bright infrared source with almost no visible light to accompany it would be like finding a smoldering campfire in a dark forest, a clear sign that something very unusual is happening. This is not just a thought experiment. Astronomers are actively conducting these searches right now, sifting through data from infrared space telescopes like NASA's, a Wide-Field Infrared Survey Explorer or WISE. They have scanned the entire sky, cataloging hundreds of millions of objects, and their computers are programmed to hunt for exactly these kinds of anomalous stars. The search has turned up some truly perplexing candidates. One of the most famous is a star known as KIC 8462852, or more popularly, Tabby's star. For years, data from the Kepler telescope showed that this star underwent bizarre, irregular dimming events, sometimes dipping in brightness by up to 22%. These dips were far too extreme to be caused by a planet, and their irregular pattern didn't match any known stellar behavior. While the leading explanation now points to clouds of dusty debris, the initial mystery was so profound that a Dyson sphere-like megastructure was seriously considered as a potential, though unlikely, explanation. The very fact that scientists were willing to entertain such a fantastical idea shows how seriously this field is now taken. The ongoing hunt isn't for a fully completed sphere, but for partial swarms, or even just the industrial byproducts of a civilization that is still under construction. Each anomalous star that can't be explained by natural astronomy is a clue, a flicker of possibility that somewhere in the dark, a species has learned to build on a scale that dwarfs our greatest achievements, rearranging the very architecture of its solar system and sending a silent, thermal beacon across the cosmos. Now, let's shift our focus from the slow, silent engineering of Dyson spheres to a phenomenon that is anything but slow: sudden, unimaginably powerful blasts of energy that flash across the cosmos in the blink of an eye. These are fast radio bursts, or FRB, and they represent one of the most electrifying and perplexing puzzles in modern astronomy. Picture this: a single, fleeting burst of radio waves, lasting only a few thousandths of a second, yet releasing more energy in that instant than our Sun does over several days. These are not gentle signals, they are cosmic screams, colossal explosions of radio light that travel for billions of years across intergalactic space before being picked up by our most sensitive radio telescopes here on Earth. The sheer power involved is staggering, forcing us to confront the question: what kind of natural engine could possibly produce such a brief, violent, and brilliant flash? When FRBs were first discovered in archival data in 2007, they were so unexpected and bizarre that many astronomers initially questioned whether they were some kind of terrestrial interference or an instrumental glitch. But as more and more were detected, their extragalactic origin was confirmed. These bursts were coming from far beyond our Milky Way, from distant galaxies millions or even billions of light years away. The mystery deepened with the discovery that some of these bursts are one-off events, a single, magnificent pop in a specific patch of sky that is never heard from again. Others, however, are repeaters, firing off multiple bursts from the same location, sometimes in a frantic, storm-like sequence and sometimes in a quiet, unpredictable pattern. This distinction between one-offs and repeaters immediately suggested that there might be more than one type of source capable of creating these extraordinary events. The hunt for a natural explanation has been incredibly fruitful, leading us to one of the most extreme and magnetic objects in the universe, magnetar. A magnetar is a type of neutron star, the collapsed, ultra-dense core of a massive star that went supernova. But a magnetar is a neutron star on steroids, possessing a magnetic field so powerful it defies comprehension, 1 trillion times stronger than Earth's field. This unimaginable magnetism creates immense stress on the star's crust. Occasionally, this crust can fracture in a starquake, a seismic event that releases titanic amounts of energy and can blast out a brilliant flash of radio waves across the cosmos. In 2020, astronomers witnessed what many consider a smoking gun, a tremendously powerful FRB that originated from a known magnetar within our own galaxy. This observation provided the first direct evidence linking at least some FRBs to these incredible cosmic powerhouses, finally giving a solid, natural explanation for a significant portion of these mysterious signals. Yet the story is far from over. While magnetars explain many FRBs, they cannot easily account for all of their bizarre properties. Some repeating bursts show patterns that are highly organized, and others emit energy across an astonishingly wide range of frequencies, which is difficult to explain with simple starquake models. It is this lingering strangeness, this remaining sliver of the unexplained, that keeps a more speculative and utterly fascinating door open. Could some FRBs, particularly the most energetic or strangely patterned ones, be artificial in origin? This is not the mainstream view, but it is a possibility that serious scientists are willing to consider, if only to rule out every conceivable alternative. The idea is that an advanced civilization, one far beyond our own technological capabilities, might need to generate immense amounts of power for interstellar communication or even for propulsion. Consider the concept of a light sail, similar to what was proposed for Oumuamua, but on a truly gargantuan scale. To propel a massive spacecraft to a fraction of the speed of light, you would need a colossal energy source. One theoretical method would be to focus an incredibly powerful beam of energy, for instance, a tightly focused radio beam, onto a sail from a fixed location. Now, from our distant vantage point, as that beam sweeps across the sky, we wouldn't see the sail or the spacecraft. We would only see a fleeting, incredibly bright flash of radio energy as the beam momentarily points in our direction. It would be like a cosmic lighthouse, and we would be seeing a single, blinding pulse as the rotating beam passes over us. The properties of such an artificial beam could neatly match the profile of an FRB, an ultra-bright, ultra-short burst that appears to come from a single point in a distant galaxy. This line of thinking was famously explored with a specific FRB discovered in 2015, known as FRB 121102. This burst was a repeater, and for a time, its bursts seemed to show a strange, repeating pattern in their timing. While this pattern was later found to be less strict than initially thought, and is now attributed to complex astrophysics, it sparked a crucial debate. It forced astronomers to ask, how would we even distinguish a natural cosmic event from an artificial one? The answer lies in the details hidden within the signal itself. A naturally occurring burst, even from a magnetar, will have certain predictable characteristics dictated by plasma physics and the magnetic fields it travels through. An artificial signal, however, might be too clean. It could be confined to an unnaturally narrow band of frequencies, or it might carry a form of encoding or modulation that doesn't occur in nature. As our telescopes become more advanced, we are not just cataloging these bursts, we are forensically dissecting them, looking for any tiny anomaly, any single detail that breaks the known laws of physics, which could be the hint that we are not just listening to the universe's natural fireworks, but to something else entirely. The search for fast radio bursts is a perfect example of how modern science operates, diligently solving mysteries with natural explanations while remaining open to the breathtaking possibility that the universe might still have a few artificial surprises in store. So far, we've talked about the habitable zones around stars, but what if the very location of a star within its galaxy is just as critical for the emergence of intelligent life? This brings us to a grander, more expansive concept, the galactic habitable zone. Imagine the Milky Way not as a uniform swirl of stars, but as a vast metropolis with distinct neighborhoods, some far more conducive to a long, prosperous civilization than others. The galactic habitable zone is that prime cosmic real estate, the ring within a spiral galaxy where the conditions align to support not just simple life, but the long-term evolution of complex, intelligent beings. It's a delicate balancing act of chemistry, location, and cosmic safety, and our own solar system appears to be sitting in one of the very best seats in the house. The first crucial ingredient in this galactic recipe is metallicity, which in astronomy has nothing to do with rock music, but everything to do with the abundance of elements heavier than hydrogen and helium. These metals, as astronomers call them, are the essential building blocks for rocky planets like Earth. They are forged in the nuclear furnaces of massive stars and are then scattered across space in the spectacular explosions of supernova. Without a sufficient supply of these elements, a planetary system would consist mostly of gas giants, with no solid, terrestrial worlds on which life could take root. The inner regions of the galaxy, closer to the bustling core, have a much higher metallicity because stars have been forming, living, and dying there for billions of years, enriching the cosmic environment with these heavy elements. Our Sun, located about 27,000 light-years from the galactic center, resides in a region with a perfect metallicity Goldilocks zone, not so metal-poor that rocky planets can't form, and not so metal-rich that the system would be bombarded with too much radiation. This positioning gave us the fundamental material to build a world like Earth in the first place. But having the right building materials is only half the battle. You also need a relatively peaceful environment to assemble them over billions of years. This is where our location away from the galactic core becomes a monumental advantage. The center of the Milky Way is an incredibly dense and violent place, packed with stars orbiting a supermassive black hole. The sheer gravitational chaos in this region would likely disrupt the stable orbits of planets, flinging them into interstellar space or sending them on collision courses. More dangerously, the galactic center is a maelstrom of intense radiation from countless stellar nurseries, neutron stars, and the central black hole itself. This constant, high-energy barrage would make it incredibly difficult for life to arise or for a planet to hold onto its protective atmosphere. By residing in the galaxy's quieter suburban disk, our solar system enjoys a much more stable and tranquil orbit, shielded from the relentless turmoil of the downtown core. The final and perhaps most dramatic threat comes from cosmic cataclysms, supernova and gamma-ray bursts. A nearby supernova is one of the most violent events in the universe, and if one were to occur within a few dozen light-years of Earth, it would be an extinction-level event. The blast of high-energy radiation and cosmic rays would strip away our ozone layer, bathe the planet in deadly radiation, and potentially trigger a global ice age. Gamma-ray bursts, the most energetic explosions known, are even more devastating. A direct hit from one within thousands of light-years could sterilize large portions of a galaxy. The frequency of such events is not uniform throughout the Milky Way. In the crowded inner galaxy and in the active spiral arms where massive stars are constantly being born and quickly dying, the risk is far greater. Our solar system, however, occupies a fortunate position. We are not in a densely packed star cluster, and our orbit around the galaxy happens to be remarkably circular, keeping us consistently in between the major spiral arms for long periods. This allows us to avoid the stellar nurseries where these short-lived, massive stars, the ones that die as supernova, are most commonly found. We are, in a very real sense, living in a galactic safe zone, a quiet backwater that has been largely insulated from the universe's most frequent and destructive tantrums. When you overlay all these factors, the right metallicity for planet building, a safe distance from the chaotic center, and a location that minimizes the risk of nearby stellar explosions, you get a surprisingly narrow ring within the Milky Way. This is the galactic habitable zone, and it's a concept that is both empowering and profoundly humbling. It suggests that even within a galaxy of hundreds of billions of stars, the number of worlds that have enjoyed the same long-term cosmic stability as Earth might be far smaller than we once imagined. Our position isn't just random luck, it's a prerequisite for our existence. The fact that we are here to ponder this question is a direct consequence of our place in this galactic sweet spot. It forces us to consider that while simple microbial life might be scattered throughout the cosmos, the evolution of beings capable of looking up and understanding the galaxy they inhabit may require a very specific and perhaps rare cosmic address. But what if the most telling evidence for life in the cosmos isn't found by peering through a telescope, but by looking down deep into the most hostile corners of our own planet? For generations, we operated under a narrow assumption about the conditions necessary for life, a concept often called the comfort zone. We believed life required a gentle mix of sunlight, moderate temperatures, liquid water, and neutral acidity. Then we began discovering organisms that weren't just surviving in places we considered hellish. They were thriving, fundamentally rewriting the biological rulebook. We call these incredible life forms extremophiles, and their very existence has shattered our preconceived notions, forcing us to dramatically expand the map of potential habitats across the entire solar system and beyond. Consider the deep-sea hydrothermal vents, often called black smokers. These are not gentle hot springs, they are geological power plants located thousands of feet below the ocean's surface in a world of perpetual, crushing darkness. Here, superheated water, reaching temperatures well over 700 degrees Fahrenheit, erupts from chimneys of mineral-rich rock, creating a toxic brew laden with heavy metals and sulfur. For any conventional organism, this environment would be instantly lethal. Yet, these vents are oases of life. Towering tube worms, some over 8 feet long, cluster around the plumes, while blind white crabs and strange, ghostly shrimp scuttle across the seafloor. The foundation of this entire ecosystem is not photosynthesis but chemosynthesis. Microbes at the base of this food chain possess the incredible ability to extract energy from the chemical bonds of hydrogen sulfide, the very compound that makes the vent fluid poisonous. They turn this geological poison into biological fuel, supporting a complex community completely independent of the sun's energy. The profound implication for astrobiology is immediate and stunning. If an entire, thriving ecosystem can exist in total darkness, powered by geology and chemistry alone, then ocean worlds like Europa and Enceladus, with their subsurface oceans and likely hydrothermal activity, are not just frozen wastelands. They are potential paradise for exactly this kind of life. The resilience of life doesn't stop at the ocean floor. We have found microorganisms known as endoliths, which literally means inside rock, that have taken this tenacity to an even more radical extreme. These tiny life forms burrow into the solid, crystalline structure of rocks, dwelling in microscopic pores and fractures deep beneath the surface. They are found in the bone-dry valleys of Antarctica, within volcanic basalt on the ocean floor, and even miles down in gold mines, where they survive on the faint trickle of chemical energy released from the surrounding stone, in total isolation from the world above. Some of these microbial communities are estimated to be thousands of years old, living in a state of suspended animation, their metabolism slowed to a geological pace. This discovery completely redefines the subsurface as a habitat. We now know that a planet doesn't need a pleasant surface environment with lakes and an atmosphere to host life. A world like Mars, with a radiation-scorched and frozen surface, could very easily have a vast, deep subsurface biosphere where endolithic microbes have retreated and persisted for billions of years, safe from the harsh conditions above. The entire concept of a habitable world now includes the kilometers of rock beneath our feet. Then there are the acidophiles, organisms that not only tolerate but require intensely acidic conditions to live. In places like the Rio Tinto in Spain, a river with water the color of red wine and a pH level comparable to stomach acid, we find a vibrant ecosystem of algae, fungi, and bacteria flourishing. These organisms have evolved specialized cellular machinery to pump out protons and maintain a stable internal pH, effectively building a fortress against a corrosive environment. This has a direct and powerful parallel to the clouds of Venus. While the surface of Venus is infernally hot, its upper cloud decks have a more moderate temperature, but they are composed of droplets of sulfuric acid, a substance that would dissolve most life on Earth. The discovery of acidophiles here proves that life can indeed engineer a way to exist within such a caustic medium. It provides a plausible biological blueprint for how hypothetical, airborne microbes could survive and even prosper in the Venusian skies, turning a seemingly insurmountable obstacle into a potential home. Each new extremophile we discover is like finding a key that can unlock another door in the cosmos. We have found psychrophiles, microbes that thrive in the permanent frost of the Arctic, metabolizing slowly at temperatures far below freezing. We have discovered radiophiles like the bacterium Deinococcus radiodurans, which can withstand doses of ionizing radiation thousands of times greater than what would kill a human, effortlessly repairing its shattered DNA. There are even tardigrades, which we've already met, that can survive the vacuum of space itself. This incredible tapestry of resilience tells a single, unifying story. Life is not a fragile phenomenon. It is a stubborn, opportunistic, and incredibly creative force. Once it gains a foothold, it adapts, evolves, and finds a way to persist in the most unthinkable conditions. This doesn't just suggest that life might exist elsewhere. It strongly implies that if the basic ingredients are present, liquid water, a source of energy, and the right chemistry, then life is not just a possibility but a probable outcome. The extremophiles of Earth are our most powerful guides, showing us that the universe is likely filled with life, not as we know it, but as we are only just beginning to imagine it. While we've explored the possibility of detecting the colossal engineering of advanced civilizations, the search for more direct communication continues with unprecedented focus and funding, moving from theoretical concepts to a practical, data-driven hunt. This brings us to one of the most ambitious scientific endeavors ever conceived, a project that has fundamentally reshaped the search for extraterrestrial intelligence, or SETI. The Breakthrough Listen initiative, launched in 2015 with a staggering $100 million commitment from investors Yuri and Julia Milner, represents a quantum leap in our quest to find our cosmic neighbors. For decades, SETI was often a side project, piggybacking on telescope time and operating on a shoestring budget, susceptible to the whims of government funding cycles. Breakthrough Listen changed the game entirely, transforming SETI into a mainstream, large-scale, and systematic science. It's not just listening for a lucky signal. It's conducting a comprehensive digital census of the cosmos, scanning the sky with a level of sensitivity and scope that was once pure fantasy. The project's power comes from its access to some of the most formidable astronomical instruments on the planet. It employs a multi-pronged approach, using the Green Bank Telescope in West Virginia, the largest fully steerable radio telescope in the world, and the Parkes Observatory in Australia, to scan the entire galactic plane and the center of our Milky Way. It also utilizes the automated Robert C. Bayard Green Bank Telescope and the Lick Observatory's automated planet finder in California to search for optical laser transmissions. This multi-wavelength strategy is crucial because an advanced civilization might not be using the technology we expect. They could be broadcasting with powerful radio waves, or they might be using highly focused, pulsed laser beams for efficient interstellar communication, a form of signaling that would stand out sharply against the natural background of starlight. By covering both bases simultaneously, Breakthrough Listen maximizes its chances of catching a signal, no matter what form it takes. But what truly sets this initiative apart is its sheer scale and methodological rigor. The project is not just pointing at a few hundred promising stars, it is systematically surveying the 1 million stars closest to Earth, scanning the entire plane of our Milky Way galaxy, and even listening to the 100 closest galaxies to our own. The volume of data it collects is almost incomprehensible. Every day, the telescopes gather multiple petabytes of information, which is more data than is contained in the entire printed collection of the Library of Congress. To sift through this cosmic haystack, the project employs sophisticated algorithms and machine learning techniques to filter out the constant radio chatter from human technology, cell phones, satellites, and radar, and identify any signal that exhibits the telltale signs of an artificial origin. These signs include a narrow bandwidth, meaning the signal is focused on one very specific frequency, unlike the broad-spectrum emissions of natural cosmic objects. Another clue is a signal that drifts in frequency in a way consistent with the Doppler shift caused by a transmission originating from a planet rotating on its axis and orbiting its star. Finding a signal that checks all these boxes would be the discovery of the millennium. The philosophy behind Breakthrough Listen is one of open science and global collaboration. All of the data collected is made publicly available, allowing astronomers, citizen scientists, and even curious students from around the world to download and analyze it, turning the search for extraterrestrial intelligence into a truly global effort. This has already led to several intriguing, though ultimately explainable, candidates that sparked intense follow-up observations. While no confirmed alien signal has been found yet, the project has already placed the most stringent limits ever on the prevalence of advanced civilizations in our galactic neighborhood. We now know, for instance, that there are no powerful, continuous transmitters beaming signals directly at us from any of the thousands of star systems surveyed so far. This negative result is, in itself, a profound piece of scientific knowledge. It tells us that if intelligent civilizations are out there, they are not flooding the galaxy with omnidirectional radio broadcasts, perhaps because such a method is incredibly energy inefficient. They might be using more targeted, intermittent, or advanced forms of communication that we are only just beginning to learn how to detect. The legacy of Breakthrough Listen extends far beyond its own data archives. It has revitalized the entire field of SETI, providing it with financial stability and scientific credibility, and inspiring a new generation of researchers. It serves as a powerful technological testbed, driving innovations in signal processing, data management, and telescope networking that benefit all of astronomy. Most importantly, it embodies a fundamental shift in humanity's place in the cosmos. For the first time, we are not just passively wondering about life out there. We are actively, systematically, and persistently listening for it with the best tools at our disposal. This project is a statement of intent, a declaration that we are a curious species ready to reach out, and that we have built the ears to hear a reply if one ever comes. It transforms the search from a question of if we will find a signal to a question of when we will process the right piece of data on the right day and hear the whisper that changes everything. Next, our cosmic investigation takes us to the jewel of the Jovian system, a world that has fascinated astronomers for generations, Jupiter's moon Europa. From a distance, it looks like a cracked marble, a smooth, icy sphere crisscrossed with dark, rusty lines. For a long time, scientists theorized that beneath this frozen shell lay a global liquid water ocean, kept from freezing by the immense tidal forces generated by Jupiter's gravity. But a theory, no matter how compelling, needs proof. Then, the Hubble Space Telescope delivered something extraordinary. On multiple occasions, Hubble's keen eye detected faint, transient plumes of water vapor spewing into space from Europa's south polar region. Imagine a colossal geyser on Earth, but one that erupts in the profound cold and vacuum of space, shooting material over 100 miles high before it falls back to paint the moon's surface. These aren't constant features, they are intermittent, flickering on and off like a celestial beacon that only occasionally shines. This discovery transformed Europa from a world of immense potential into a world of immediate, tangible opportunity. The significance of these plumes cannot be overstated. They act as a direct sample return system operated by nature itself. Europa's subsurface ocean is hidden beneath an ice crust estimated to be many miles thick. Drilling through that much ice is a monumental engineering challenge far beyond our current capabilities, but these plumes offer a breathtaking shortcut. If a spacecraft could fly through one of these erupting columns, it could literally taste the contents of the hidden ocean. Its onboard instruments could analyze the water vapor and any frozen particles for salts, organic compounds, and just maybe direct chemical or even biological signatures of life. It's the difference between trying to dig a well to a deep aquifer and simply catching rain from a passing storm. The plumes provide a free and direct delivery of material from the environment we are most desperate to study. This changes the entire game for astrobiology, turning a decades-long goal into a near-future possibility. Of course, with a discovery this profound comes a vigorous scientific debate about the source of these plumes. The leading hypothesis points to the same tidal heating that keeps the ocean liquid. As Europa orbits Jupiter in a slightly elliptical path, the planet's ferocious gravity constantly stretches and squeezes the moon, generating immense internal heat. This process could create pockets of slushy ice or even lakes of liquid water trapped within the icy crust itself. The stress from this tidal flexing might cause these reservoirs to periodically rupture, sending their contents jetting out into space through cracks in the ice. Another compelling theory suggests the plumes could be fueled by shallow, subsurface water, perhaps warmed by hydrothermal activity on the ocean floor, rising through the crust and erupting at weak points. Each model has its merits, and determining which is correct is crucial because it tells us about the accessibility and the chemistry of the ocean below. A plume fed by a deep ocean source would carry a far richer and more representative sample than one coming from a small, isolated pocket just beneath the surface. This thrilling prospect is the entire driving force behind one of the most anticipated missions in the history of space exploration, NASA Europa Clipper. Scheduled to arrive at Jupiter in the 2030s, Clipper is not an orbiter in the traditional sense. It will perform a complex dance, making nearly 50 close flybys of Europa to minimize its exposure to the brutal radiation belt surrounding Jupiter. It is a spacecraft built as a dedicated detective, armed with a suite of 9 powerful instruments designed to work in concert. Its cameras will map the surface in unprecedented detail, looking for fresh plume deposits and active venting. Its spectrometers will analyze the composition of both the surface and any plumes it encounters, searching for organic molecules. But perhaps most crucially, its radar instrument will peer through the icy shell, measuring its thickness and searching for those potential subsurface lakes, effectively giving us a sonogram of the moon to understand the plumbing system that feeds these incredible eruptions. The mission strategy is one of agile opportunism. Europa Clipper will be listening and watching constantly, ready to adjust its trajectory on the fly if it detects a plume erupting. During a flyby through a plume, its mass spectrometer will perform a direct chemical analysis of the particles, telling us the salinity of the ocean and identifying complex carbon-based molecules. Finding the right mix of chemicals such as salts matching Earth's oceans, a source of energy like hydrogen sulfide, and the building blocks of life like amino acids would be a powerful indicator that the ocean is not only habitable but perhaps even inhabited. The mission will essentially assess the habitability of Europa's ocean, laying the groundwork for the ultimate future step, a lander that could potentially touch down near a plume deposit, analyze the fresh material, and search for definitive evidence of life. Every time Hubble or ground-based telescopes see another flicker of activity at Europa, it reinforces the stunning reality that we are on the verge of exploring an alien ocean, not with a drill, but with a cup held out to catch the cosmic spray from a world that may be waiting to tell us we are not alone. For all the mounting evidence that seems to point toward a universe teeming with life, there exists a powerful and sobering counter-argument, a concept that forces us to consider the possibility that our vibrant, complex world is a cosmic fluke of almost unimaginable rarity. This is the rare Earth hypothesis. It doesn't argue that simple microbial life is impossible elsewhere. Rather, it posits that the dizzying series of specific, fortunate circumstances required for that life to evolve into complex, intelligent, technological beings like us is so exceptionally unlikely that we might be virtually alone in the galaxy, if not the entire universe. Proponents of this view point to a long and daunting checklist of prerequisites that Earth just happened to satisfy perfectly. We orbit at just the right distance from a stable, long-lived star. We have a massive moon formed from a freak planetary collision in the early solar system, which stabilizes our axial tilt, preventing chaotic climate swings that would otherwise make long-term evolution impossible. Our planet has active plate tectonics and a strong magnetic field, which recycle nutrients and shield the surface from lethal cosmic and solar radiation. We reside in the safe, galactic suburbia we discussed earlier, far from the sterilizing blasts of nearby supernova, and we've enjoyed hundreds of millions of years of relative planetary stability, allowing for the slow, unbroken march from single-celled organisms to conscious spacefaring beings. The rare Earth argument suggests that this isn't just a simple checklist, but a chain of interdependent miracles, where if any one link had been broken, we would not be here to ponder our existence. Yet for every point on the rare Earth checklist, the torrent of data from modern astronomy seems to provide a compelling counterpoint, forcing a dramatic re-examination of this hypothesis. The most powerful rebuttal comes from the sheer, staggering numbers revealed by exoplanet science. For centuries, we had a sample size of one, our own solar system. We didn't know if planets were common or rare. Now we know. Current estimates extrapolated from Kepler telescope data suggest there are more planets than there are stars in our galaxy, with billions of these worlds likely being rocky, Earth-sized bodies orbiting within their star's habitable zone. The numbers alone are a powerful argument against uniqueness. When you have hundreds of billions of potential candidates, even the most unlikely of events becomes statistically plausible. It's like shuffling a deck of cards. The probability of getting one specific, highly ordered sequence is astronomically small. But if you shuffle that deck enough times, that precise sequence will eventually appear. Our galaxy has been shuffling the planetary deck for over 10 billion years, providing an almost limitless number of opportunities for another winning hand to be dealt. Furthermore, the rare Earth hypothesis was largely formulated before we truly understood the incredible tenacity of life itself, the world of extremophiles we just explored. The hypothesis often assumes that life requires a gentle, Earth-like cradle to arise and thrive. But we now know that life is not a delicate flower. It is a stubborn, opportunistic weed that can take root in the most hostile environments imaginable. The discovery of entire ecosystems thriving in total darkness around hydrothermal vents, of microbes living miles deep within solid rock, and of organisms flourishing in boiling acid or freezing brine, fundamentally challenges the notion that life needs a perfect, narrow set of conditions. This resilience dramatically expands the real estate for simple life in the cosmos. A planet doesn't need a large moon, plate tectonics, or even a stable climate for microbial life to emerge and persist. It just needs a persistent energy source and liquid water. And as we've seen on Enceladus, Europa, and even in the subsurface of Mars, liquid water can exist in a surprising number of places far outside the traditional habitable zone. This brings us to the crucial distinction that may be the key to resolving this debate: the difference between the emergence of life and the evolution of complex, intelligent life. The rare Earth hypothesis might be correct in its assertion that the progression from microbes to a technological civilization is an incredibly difficult and fragile journey, fraught with evolutionary bottlenecks and planetary perils. Mass extinction events like the asteroid impact that wiped out the dinosaurs show how easily the thread of complex evolution can be severed. It's entirely possible that while microbial life is a common, hardy cosmic phenomenon, flourishing in subsurface oceans and within the crust of countless worlds, intelligent, tool-using life is the true rarity. The universe may be a quiet, mostly microbial place, filled with planets where life got started but never made the leap to multicellular complexity, or did so only to be wiped out by a cosmic catastrophe before it could look to the stars. In this view, the silence of the cosmos, the fact that we haven't yet detected any clear signals from other civilizations, isn't a sign that life is rare, but that civilizations are ephemeral and isolated. Ultimately, the ongoing dialogue between the rare Earth perspective and the new findings of exoplanetology and astrobiology is one of the most productive tensions in modern science. It forces us to refine our questions and sharpen our search strategies. It reminds us that the discovery of a single, fossilized microbe on Mars or in the plumes of Enceladus would be a universe-altering event, confirming that life is a natural cosmic process, while still leaving open the profound question of whether consciousness is a rare spark or a common destination. This isn't a debate with a simple winner or loser. It is a framework that guides our exploration, pushing us to look not just for Earth twins, but for the incredible diversity of habitats where life, in its most resilient and fundamental forms, might have found a way. The answer may lie not in proving one side entirely right, but in discovering that the cosmos is both a bustling garden of simple life and a vast, quiet cathedral where complex, intelligent voices are separated by immense gulfs of both space and time. But our search for cosmic company cannot be limited to listening for radio whispers or analyzing atmospheric chemistry. What if an entire civilization is broadcasting its existence not through intentional messages, but simply through the colossal, unintentional byproducts of its industry and daily life? This brings us to the thrilling frontier of searching for technosignatures, the physical and technological evidence of an advanced society. Think of it this way: if you were an alien astronomer observing Earth from a distant star, you wouldn't necessarily need to decode our television broadcasts to know we are here. You could simply detect the glow of our cities lighting up the night, the specific chemical pollutants from our factories lingering in our air, or even the faint constellation of thousands of satellites swarming our planet. These are all technosignatures, and they offer a powerful new way to hunt for intelligence that might not be trying to communicate, but is simply too busy being a civilization to hide its presence. One of the most poetic and direct technosignatures to search for is the artificial glow of city lights on the dark side of an exoplanet. Imagine a world tidally locked to its star, with one hemisphere in permanent, scorching daylight and the other in an eternal, frozen night. A natural world would be almost completely dark on that night side, with only the faint shimmer of auroras or occasional lightning strikes to break the blackness. But if a technological species lived there, they would almost certainly congregate on the temperate border between the two extremes, the terminator line, and they would need artificial light to illuminate their cities during the long night. Our most powerful next-generation telescopes, like the planned LUVOIR or HAB-X space observatories, will have the capability to measure the minute difference in brightness between a planet's day side and its night side. If they were to observe an Earth-like world and find that its night side is significantly brighter than it should be, glowing with a distinct artificial spectrum unlike any natural aurora or volcanic glow, it would be a stunning revelation. It would be like looking across the interstellar void and seeing the unmistakable collective streetlights of an alien metropolis, a silent testament to a society that has mastered its environment. Beyond the simple need for light, an advanced civilization would inevitably leave a chemical fingerprint on its world, a signature of its industrial activity. Here on Earth, our atmosphere contains telltale gases that have no significant natural source. The most prominent of these are chlorofluorocarbons, or CFC. These are entirely synthetic compounds invented in the 20th century for use in refrigeration and aerosols. They are also devastatingly effective at destroying ozone and are powerful greenhouse gases. While we now regulate them because of their environmental impact, their presence in our air is a clear technosignature. An alien astronomer with a spectrometer powerful enough to analyze our atmosphere would see these CFCs and know immediately that they are looking at a planet with an industrial civilization. Similarly, the persistent global presence of nitrogen dioxide from combustion processes or high levels of methane from agriculture and waste management would paint a picture of a planet deeply shaped by technological activity. The search for such industrial pollution is already a serious scientific pursuit. When the James Webb Space Telescope analyzes the atmosphere of a distant world, it's not just looking for the gentle balance of oxygen and methane that might suggest bacteria. It is also capable of detecting the harsh, unnatural spike of CFCs or other industrial pollutants. Finding such a signature would be arguably an even more profound discovery than a biological one, as it would point not just to life, but to a society that has reached a level of technological development mirroring or perhaps far surpassing our own. Perhaps the most futuristic and subtle technosignature of all would be the detection of artificial structures orbiting a distant world. We are already creating this signature ourselves. The growing cloud of satellites encircling Earth, including mega constellations like Starlink, is beginning to form a faint, detectable ring around our planet. From an immense distance, this wouldn't look like individual points of light, but rather like a thin, shimmering band that slightly alters the way light reflects from our world. Now imagine a civilization that is centuries or millennia more advanced than us. They might have constructed vast orbital habitats, solar power stations, or swarms of manufacturing platforms that form a dense, intricate ring system around their planet. When that planet passes in front of its host star, these artificial rings would cause a unique, complex pattern of dimming. Unlike the smooth, symmetrical dip caused by a natural gas giant's rings, the dimming from an artificial swarm would be jagged, irregular, and might even show repeating patterns that betray its designed, non-random structure. Furthermore, these structures would reflect a different color and spectrum of light than natural ice or dust. The hunt for such signatures is a long-term game, requiring incredible precision, but it fundamentally expands the definition of what we are looking for. We are no longer just searching for biology or even planetary-scale pollution. We are searching for the literal architecture of an advanced civilization, the physical proof that a species has expanded beyond its home world and begun to reshape its immediate cosmic environment. The beauty of the technosignature approach is that it bypasses the need for a civilization to be actively and intentionally trying to talk to us. A society might be completely inward-focused, or it might use forms of communication we cannot yet conceive, like quantum entanglement or neutrino beams. But it would be nearly impossible for a globally active, technological species to completely hide the energy demands and physical artifacts of its existence. The lights of its cities, the chemistry of its industry, and the infrastructure of its orbit are all silent, unintentional broadcasts proclaiming, "We are here." This shifts the search from a game of interstellar conversation to one of cosmic forensics, where we become detectives sifting through the physical evidence of distant worlds, looking for any clue, however small, that one of them is not just inhabited but built. Now, to truly appreciate the potential for life to arise across the cosmos, we must travel back in time, not with a time machine, but with a telescope so powerful it can see the infant universe. This brings us to a profound discovery that is less about finding a specific biosignature and more about understanding the very foundation of life's possibility. The James Webb Space Telescope was designed to be a cosmic time machine, and it has already begun to revolutionize our view of the universe's childhood by spotting the first galaxies and stars that flickered into existence. What does this have to do with the search for life? Everything. Because these early observations reveal a stunning and critical truth. The universe got its act together with breathtaking speed, manufacturing and distributing the essential elements for life almost as soon as it possibly could. For life as we know it to exist, you need more than just hydrogen and helium, the primitive elements forged in the Big Bang. You need a rich periodic table. You need carbon, the backbone of organic chemistry, oxygen, a key component of water and air, nitrogen, a fundamental element in our DNA, and phosphorus, a crucial ingredient in our energy-carrying molecules. These heavier elements, which astronomers call metals, are not born in the Big Bang. They are forged in the nuclear furnaces of stars and then scattered across the cosmos in the violent, spectacular deaths of those stars as supernova. For generations, we assumed this process of cosmic enrichment was a slow, gradual one. We thought the first stars were massive behemoths that lived fast and died young, seeding the void with the first heavy elements, and that it took billions of years for subsequent generations of stars to build up enough of these elements to form rocky planets and the chemistry for life. The early universe, we believed, was a metal-poor wasteland, likely incapable of supporting the complex chemistry that life requires. The James Webb Space Telescope has completely overturned that slow and steady narrative. Its deepest images, like those from the Jade Survey, have revealed fully formed galaxies when the universe was only a few 100 million years old, a mere blink of an eye in cosmic terms. Even more astonishingly, spectroscopic analysis of the light from these incredibly ancient galaxies has already detected the signatures of carbon, oxygen, and neon. This is a paradigm-shifting discovery. It means that the first generations of stars worked with ferocious efficiency, producing and dispersing the building blocks of life on a galactic scale far earlier than any model had predicted. The cosmic kitchen was open for business almost immediately, and it was serving a rich soup of complex elements right from the start. The universe did not wait around. It began constructing the ingredients for planets and life when it was just 1 or 2% of its current age. This dramatically resets the clock for the potential emergence of life in the cosmos. If the necessary elements were available so early, then the first potentially habitable rocky planets could have formed around some of the universe's very first stars over 13 billion years ago. That is 9 billion years before our own solar system even began to coalesce from a cloud of stardust. Let that sink in for a moment. While our Earth is a relative newcomer at 4.5 billion years old, the universe may have been producing Earth-like worlds for billions of years prior. This expansive timeline completely changes the equation for the development of life and intelligence. It grants biology an almost unimaginable head start. On some of those ancient worlds, life could have arisen, evolved, and perhaps even given rise to civilizations that rose and fell during epochs when Earth was still a molten ball of rock. The silence we perceive today might not be because life is rare, but because we are the latecomers arriving at the party long after the most vibrant conversations have ended, listening for echoes in a galaxy that may have been bustling with activity for eons before we were even a twinkle in the Milky Way's eye. This new timeline also forces us to reconsider the very nature of those first life-bearing environments. They would have been profoundly different from our own. Their host stars would have been made almost entirely of hydrogen and helium, with just that first sprinkling of heavier elements. Their planetary systems would have been metal-poor by our standards, and they would have existed in a more compact, violent universe with a higher risk of nearby gamma-ray bursts and supernova. Yet the James Webb data tells us the ingredients were there. Life, as extremophiles on Earth have shown us, is incredibly resourceful. It may have found a way in those alien cradles, evolving along paths we can scarcely imagine. By revealing the unexpected chemical maturity of the infant cosmos, the James Webb Space Telescope has done more than just show us ancient galaxies. It has fundamentally expanded the window of opportunity for life, suggesting that the story of biology in the universe is not only vast in space, but also incredibly deep in time, opening up possibilities that make our search for cosmic companions both more humbling and more thrilling than ever before. All of the evidence we've gathered so far paints a compelling picture of a universe that seems perfectly capable of hosting life. And yet, when we listen for the voices of other intelligent civilizations, we are met with a profound and puzzling silence. This contradiction is the heart of the Fermi paradox, famously encapsulated by the physicist Enrico Fermi's simple, cutting question: where is everybody? If the cosmos is so vast and so old, and the ingredients for life are so common, then the galaxy should be teeming with intelligent species, their presence as obvious to us as the lights of a city from a nearby hilltop. The silence we observe, therefore, is a mystery that demands an explanation, and one of the most thought-provoking answers comes not from astronomy or physics, but from a field we might call cosmic sociology. This is the cosmic zoo hypothesis, a concept that suggests the reason we haven't made contact is not because other civilizations aren't out there, but because they are deliberately leaving us alone. Imagine for a moment that you're walking through a vast, pristine wilderness, and you come across a clearing where a rare and beautiful species of bird is building an intricate nest. You stop and watch, captivated. You could easily step forward, offer the bird some twigs, or even try to communicate with it, but you don't. You remain quiet, hidden, careful not to make a sound or cast a shadow, because you understand that your interference, no matter how well-intentioned, could disrupt its natural behavior, frighten it, or alter the course of its development. You are acting as a respectful observer, allowing the natural world to unfold according to its own rules. The cosmic zoo hypothesis proposes that this is exactly humanity's situation on a galactic scale. In this view, advanced extraterrestrial civilizations are the quiet observers, and Earth, with its burgeoning technological society, is the precious, protected clearing in the cosmic wilderness. They are aware of us, perhaps have been for a very long time, but they have made a collective, ethical decision not to announce their presence or intervene in our affairs. This idea functions as a powerful potential solution to the Fermi paradox because it addresses the silence without requiring that intelligent life is impossibly rare or that all civilizations inevitably destroy themselves. Instead, it posits a universe where a mature galactic community has established a fundamental rule, a kind of prime directive, to shield developing worlds like our own from the cultural and technological shock of first contact. Why would they do this? The reasoning is both ethical and pragmatic. From an ethical standpoint, a truly advanced civilization would likely recognize the immense value of a planet's independent cultural and biological evolution. They would see our struggles, our art, our scientific discoveries, and our social development as a unique and irreplaceable chapter in the story of the cosmos. To interfere would be to spoil that natural experiment, to rob us of the chance to find our own way and define our own destiny. Pragmatically, they might also understand that a sudden, jarring encounter with a far superior intelligence could be catastrophic for us, potentially triggering global panic, shattering our religious and social structures, or causing our civilization to collapse under the weight of the knowledge that we are not the pinnacle of creation. The implications of this hypothesis are simultaneously humbling and awe-inspiring. On one hand, it places humanity in a position of cosmic infancy. We are not the masters of our domain, but rather a young species being monitored, perhaps even graded, on our ability to manage our own planet, overcome our internal conflicts, and mature technologically without self-destructing. It suggests that there is a threshold we must cross, a level of societal and ethical maturity we must achieve, before the galactic gates are opened and we are invited to join the wider community of intelligent life. What might that threshold be? It could be the achievement of sustainable global peace, the responsible stewardship of our biosphere, or perhaps the demonstration that we can venture beyond our solar system without being a destructive or aggressive force. Until we meet that standard, we remain in the zoo, allowed to develop in our own enclosure, unaware of the vast civilization just beyond the invisible bars. Of course, the cosmic zoo hypothesis is not without its own set of profound questions and criticisms. For one, it assumes a remarkable degree of unity and discipline among all potential alien civilizations. Is it really plausible that every single advanced society across the entire galaxy would agree to and perfectly adhere to such a non-interference policy? There would always be the risk of a rogue actor, a civilization that breaks the rules and makes contact for its own reasons, whether out of curiosity, malice, or a desire to proselytize. Furthermore, the hypothesis raises the unsettling possibility that we are not just in a zoo, but in a nature preserve. Are we being protected for our own benefit, or are we being cultivated, studied, or even reserved as a resource? The darker interpretations, while speculative, remind us that the motivations of a truly alien intelligence are ultimately unknowable and may not align with our own concepts of benevolence. Despite these uncertainties, the cosmic zoo hypothesis offers a uniquely hopeful and challenging perspective on our future. It reframes the great silence of the cosmos not as a void of loneliness, but as a period of probation, a test of our collective character. It gives us a goal that is far grander than merely finding other life. It challenges us to become the kind of species that is worthy of being found. Every step we take towards solving our global problems, from climate change to nuclear proliferation, every effort we make to understand the universe with humility and curiosity, could be seen as us preparing for our final exam, the day we graduate from being isolated inhabitants of a single planet to becoming citizens of a galactic community. The silence, then, is not a wall but a door, and the key to unlocking it lies not in building a bigger radio telescope, but in building a better version of ourselves. But what does it take for those scattered ingredients to actually come together and start the engine of life? This brings us to a landmark discovery that didn't happen in a distant nebula or on an alien world, but inside a humble laboratory flask, an experiment that recreated the dawn of our own planet and fundamentally changed our understanding of life's origins. In the 1950s, a young graduate student named Stanley Miller, working under his advisor Harold Urey, set up a now legendary apparatus. It was a simple, closed loop of glass tubes and flasks, but inside it, he created a miniature version of the primordial Earth. One flask held water, representing the ancient ocean. Another was filled with a mixture of gases thought to mimic the early atmosphere: methane, ammonia, and hydrogen. Then he introduced an energy source, sending repeated electrical sparks through the gaseous mixture to simulate the intense lightning storms that would have been common on the young, violent planet. The question was simple yet audacious: could the basic building blocks of life form from such simple beginnings? After just 1 week, the results were unequivocal and astounding. The once clear water in the ocean flask had turned a murky, reddish-brown. When Miller and Urey analyzed this complex chemical soup, they found it was teeming with organic compounds. Most significantly, they had synthesized several different amino acids, the very same molecules that act as the Lego blocks for constructing proteins, which are the workhorse machinery of every single living cell on Earth. This was a revelation. The Miller-Urey experiment demonstrated that under conditions that were plausible for the early Earth, the fundamental ingredients for life could arise spontaneously from non-living matter through completely natural chemical processes. It provided a powerful, tangible blueprint for how life could have gotten its start, not through a miraculous event, but through the straightforward application of chemistry and physics to a planet that was just the right kind of messy. Of course, science has evolved since the 1950s, and our models of Earth's early atmosphere have become more sophisticated. We now believe it was likely less rich in hydrogen and more dominated by carbon dioxide and nitrogen. Skeptics wondered if the Miller-Urey results were specific to their particular gas mixture. Intriguingly, when scientists later revisited the experiment using these updated atmospheric recipes, they still got the same spectacular results: amino acids formed readily. Even more compelling, they discovered that Miller had actually run a second, unpublished version of the experiment using a different setup that included a jet of steam to simulate volcanic eruptions. The vials from this forgotten experiment were rediscovered in his laboratory notebook decades later and analyzed with modern, sensitive equipment. To everyone's astonishment, they contained an even richer and more diverse array of amino acids than his original famous trial. This confirmed that the pathway from simple chemicals to life's building blocks is not a fragile, one-off fluke, but a robust and repeatable process, able to proceed under a variety of plausible early Earth conditions. The universe, it seems, has a very strong bias toward creating the chemistry of life whenever it gets the chance. This profound insight from the laboratory is powerfully echoed by our observations of the cosmos itself. The same kinds of amino acids and other probiotic molecules that Miller and Urey cooked up in their flasks have been found in the most unlikely of places. Sophisticated telescopes like the Atacama Large Millimeter Array in Chile have been pointed at vast, dark clouds in interstellar space known as molecular nebulae. Within these cosmic nurseries, where new stars and planets are condensing from dust and gas, astronomers have detected the spectral fingerprints of complex organic molecules, including the simplest amino acid, glycine. This tells us that the universe is not waiting for a stable planet to begin its organic chemistry. It is doing the work in the cold, dark void of space, on the surfaces of dust grains where simple atoms can meet and link up into more complex structures. These nebulae are essentially giant, cosmic versions of the Miller-Urey experiment, running on a scale of light years instead of inches, using the gentle energy of starlight and cosmic rays instead of electrical sparks. The connection becomes even more concrete when we hold the evidence in our hands in the form of meteorites that have fallen to Earth. The Murchison meteorite, which we discussed earlier, is the ultimate proof of this concept. It didn't just contain a few amino acids, it contained over 90 different kinds, including many of the same 20 that are used by all terrestrial life to build proteins. This is a staggering convergence. The same molecules that formed in a laboratory flask simulating Earth's infancy, the same molecules detected in distant stellar nurseries, are the exact same molecules that we find delivered to our doorstep from asteroids that have been drifting through space since the solar system's formation. This triple confirmation from the lab, the nebula, and the asteroid paints an undeniable picture. The fundamental chemical pathways that lead to life are not a unique recipe exclusive to Earth. They are a universal process, a default setting of cosmic chemistry. The universe appears to be hardwired with a tendency, a driving imperative, to create the building blocks of biology wherever the basic conditions of energy and raw materials are met. This doesn't mean that life itself is inevitable on every world, but it strongly suggests that the first and most crucial step, the creation of life's raw materials, is a common, natural, and widespread phenomenon across the cosmos. When we think of hunting for life on other worlds, our minds naturally drift to solid ground, to the rocky plains of Mars, the icy crust of Europa, or the ancient riverbeds of a distant exoplanet. But what if we've been looking in the wrong place entirely? What if the most abundant and accessible habitats for life in the universe aren't on the surface of planets at all, but suspended in the skies of gas giants? This brings us to one of the most audacious and mind-bending concepts in modern astrobiology: the search for life in the clouds. Picture the mighty Jupiter, a world with no solid surface to speak of, only a vast, churning ocean of hydrogen and helium that gradually compresses into exotic, metallic forms under unimaginable pressure. It seems like the last place you would ever find life. Yet, as we peer deeper into its swirling, banded atmosphere, scientists have identified a potential sweet spot, a layer where the temperature and pressure are surprisingly Earth-like. This isn't a stable, solid environment, but a permanent, planetary-wide aerial habitat, and it's here that we find the compelling hypothesis of a floating, cloud-based biosphere. The logic behind this idea is as elegant as it is surprising. As you descend through the upper atmosphere of a gas giant, you pass through a brutal gradient of conditions. The very top layers are exposed to intense radiation and are bitterly cold. Deeper down, the pressure rises to thousands of times that of Earth, and temperatures soar to the point of melting metal. But sandwiched between these two extremes, there exists a temperate zone. In Jupiter's case, this region is found in the cloud decks roughly 30 to 70 miles below the visible ammonia ice clouds, where temperatures range from a balmy 30 to 80 degrees Fahrenheit, and the pressure is similar to what we experience at sea level on Earth. In this strange, gaseous realm, the environment is not entirely unlike the upper atmosphere of Venus, but on a far grander and more stable scale. The key to life here wouldn't be sunlight or a solid surface, but a constant source of chemical energy and a way to stay afloat. This is where the concept of an aerial biosphere takes flight. Imagine trillions of tiny microbial organisms not unlike the extremophiles we find on Earth, but adapted for a permanent airborne existence. To survive, they would need two things: a metabolic strategy and a way to control their buoyancy. The atmosphere of a gas giant is a rich chemical soup, constantly churned by colossal storms and powerful updrafts. It contains molecules like ammonia, hydrogen sulfide, and phosphine, all of which can release energy when they react with each other. Hypothetical Jovian microbes could be chemosynthetic, deriving their energy from these atmospheric chemical reactions, much like the microbes around Earth's hydrothermal vents that thrive on sulfur compounds. They wouldn't need the sun. Their world would be an endless, three-dimensional buffet of chemical potential energy. To avoid sinking into the crushing, hot depths or rising into the frigid, irradiated upper atmosphere, these organisms could employ a number of clever strategies. They might form tiny, buoyant colonies similar to plankton in Earth's oceans. They could produce microscopic droplets of liquid or gas-filled sacs to remain suspended, or they might even have a life cycle that allows them to rise and fall with atmospheric currents, spending part of their time dormant in cooler regions and part actively metabolizing in the temperate zone. We already have a remarkable earthly analog for this kind of life, and it's not in the oceans but in our own skies. For decades, scientists have been discovering a surprising diversity of microbial life high in Earth's atmosphere, carried aloft by winds and existing in a dormant state. But more relevant are the cloud-borne microbes found in some of the most extreme environments on our planet. In the highly acidic clouds above volcanoes, researchers have found bacteria that are not just surviving, but appear to be metabolically active, potentially deriving energy from dissolved volcanic gases. This proves that a nutrient-scarce, gaseous environment is not an absolute barrier to life. If microbes can eke out an existence in the harsh, transient clouds of Earth, then the idea of a dedicated, evolutionary adapted biosphere in the vast, chemically rich, and permanently cloud-covered atmosphere of a Jupiter or a Saturn becomes a legitimate scientific possibility, not just science fiction. The implications of finding such a biosphere would be nothing short of revolutionary. It would mean that life is not only more resilient than we ever imagined, but that the total number of potential habitats in our galaxy just multiplied by an enormous factor. Think about it, our galaxy contains billions of gas giants, both within our solar system and as exoplanets orbiting other stars. Many of these hot Jupiters orbit perilously close to their suns, making their surfaces utterly uninhabitable, but their upper atmospheres might still host a temperate, life-friendly layer. If atmospheric life is possible, then every single one of these gas giants becomes a candidate for biology. We wouldn't need to find an Earth twin with just the right orbit and a stable surface. We could find life floating in the skies of countless worlds, turning the galaxy from a collection of rare, habitable dots into a vast, three-dimensional ecosystem teeming with aerial plankton. The challenge, of course, is how to detect it. A future probe, perhaps a sophisticated balloon or a glider designed to ride the jet streams of Jupiter, could be equipped with sensors to directly sample the cloud droplets, searching for complex organic molecules, isotopic imbalances suggestive of biological processing, or even the microbial cells themselves. Finding life in the clouds of a gas giant would forever change our perspective, revealing a universe where biology has taken to the skies, filling the atmospheres of giant planets with a silent, floating, and unimaginably vast living haze. But this grand cosmic search for life forces us to consider a subtle yet profoundly important factor, one that we often take for granted right here at home. When we imagine a perfect, Earth-like world orbiting in its star's habitable zone, we picture a serene blue-green marble. Yet, the very stability that allows life to flourish over billions of years may depend on a silent partner in the sky, a large moon. Our own moon is far more than a beautiful celestial companion. It is a fundamental pillar of our planet's long-term habitability. The key lies in Earth's axial tilt, that 23.5-degree lean that gives us our seasons. Without a substantial moon, this tilt would be chaotic. The gravitational pull of other planets, especially Jupiter, would gradually tug and push on Earth's axis, causing it to wobble wildly over time scales of hundreds of thousands of years. Imagine a world where the tilt shifts erratically from 0 degrees with no seasons at all to a drastic 85-degree lean, where one pole bakes in perpetual sunlight while the other freezes in an eternal, dark winter. Such extreme and unpredictable climate swings would create an environment of relentless stress, making it incredibly difficult for complex ecosystems to establish themselves and evolve toward intelligence. The constant, gentle gravitational influence of our large moon acts as a cosmic gyroscope, damping these wild oscillations and keeping our planet's tilt within a narrow, stable range. This stability provides the predictable climate patterns that allowed agriculture to develop, civilizations to rise, and for us to be here today, gazing up at the very object that made it all possible. This understanding transforms the search for habitable worlds. A planet sitting perfectly in the Goldilocks zone is a fantastic starting point, but if it lacks a large stabilizing moon, it might only be habitable for simple, resilient microbial life that can weather dramatic climatic chaos. For the long, slow, and delicate dance of evolution to produce complex forests, diverse animal life, and eventually a technological civilization, a steady planetary stage is essential. This realization has launched an entirely new and incredibly challenging frontier in astronomy, the hunt for exomoons. Finding a moon orbiting a planet in another star system is a technical feat that pushes our current observational capabilities to their absolute limit. The primary method we use, the transit technique, involves detecting the minuscule dip in a star's brightness as a planet passes in front of it. Now, try to imagine detecting the even tinier dip within that dip caused by a moon transiting just before or after the planet. It's like trying to spot a gnat flying in front of a car's headlight from a mile away, while the car itself is passing in front of a searchlight. Despite the immense difficulty, astronomers are developing sophisticated new algorithms and using observatories like the James Webb Space Telescope to scour the data for these telltale signatures. The potential reward is staggering, confirming the existence of a large exomoon around a rocky world in the habitable zone would instantly elevate that system to the top of the list of potential life-bearing candidates. Consider the possibilities such a discovery would unlock. We could have a world where the planet itself is a bit too close to the inner edge of the habitable zone, making it a little too warm, but its large moon, orbiting at a slightly greater distance, enjoys more temperate conditions. Life could potentially thrive on the moon instead of the planet, a scenario straight out of science fiction like Avatar's Pandora. Furthermore, the gravitational tug of war between a planet and a large moon drives immense tidal forces which can provide a crucial source of internal heat. We see this clearly in our own solar system with Jupiter's moon Io, the most volcanically active body we know. While Io is a tormented world, that same tidal heating, applied to a moon with a subsurface ocean like Europa, can maintain liquid water and power potential hydrothermal vent ecosystems for billions of years. An exomoon doesn't need to rely on its parent star for all its energy. The gravitational friction from its host planet can provide a reliable internal furnace, opening up habitable environments in star systems we might have otherwise overlooked. Finding a large exomoon would not just be about checking a box for stability. It would reveal a whole new class of habitats, proving that life can find a way not just on planets, but in the complex, dynamic partnerships between worlds and their lunar guardians. All of the evidence we've gathered so far paints a compelling picture of a universe that seems perfectly capable of hosting life. And yet, when we listen for the voices of other intelligent civilizations, we are met with a profound and puzzling silence. This contradiction is the heart of the Fermi paradox, famously encapsulated by the physicist Enrico Fermi's simple, cutting question: where is everybody? If the cosmos is so vast and so old, and the ingredients for life are so common, then the galaxy should be teeming with intelligent species, their presence as obvious to us as the lights of a city from a nearby hilltop. The silence we observe, therefore, is a mystery that demands an explanation, and one of the most thought-provoking answers comes not from astronomy or physics, but from a field we might call cosmic sociology. This is the cosmic zoo hypothesis, a concept that suggests the reason we haven't made contact is not because other civilizations aren't out there, but because they are deliberately leaving us alone. Imagine for a moment that you're walking through a vast, pristine wilderness, and you come across a clearing where a rare and beautiful species of bird is building an intricate nest. You stop and watch, captivated. You could easily step forward, offer the bird some twigs, or even try to communicate with it, but you don't. You remain quiet, hidden, careful not to make a sound or cast a shadow, because you understand that your interference, no matter how well-intentioned, could disrupt its natural behavior, frighten it, or alter the course of its development. You are acting as a respectful observer, allowing the natural world to unfold according to its own rules. The cosmic zoo hypothesis proposes that this is exactly humanity's situation on a galactic scale. In this view, advanced extraterrestrial civilizations are the quiet observers, and Earth, with its burgeoning technological society, is the precious, protected clearing in the cosmic wilderness. They are aware of us, perhaps have been for a very long time, but they have made a collective, ethical decision not to announce their presence or intervene in our affairs. This idea functions as a powerful potential solution to the Fermi paradox because it addresses the silence without requiring that intelligent life is impossibly rare or that all civilizations inevitably destroy themselves. Instead, it posits a universe where a mature galactic community has established a fundamental rule, a kind of prime directive, to shield developing worlds like our own from the cultural and technological shock of first contact. Why would they do this? The reasoning is both ethical and pragmatic. From an ethical standpoint, a truly advanced civilization would likely recognize the immense value of a planet's independent cultural and biological evolution. They would see our struggles, our art, our scientific discoveries, and our social development as a unique and irreplaceable chapter in the story of the cosmos. To interfere would be to spoil that natural experiment, to rob us of the chance to find our own way and define our own destiny. Pragmatically, they might also understand that a sudden, jarring encounter with a far superior intelligence could be catastrophic for us, potentially triggering global panic, shattering our religious and social structures, or causing our civilization to collapse under the weight of the knowledge that we are not the pinnacle of creation. The implications of this hypothesis are simultaneously humbling and awe-inspiring. On one hand, it places humanity in a position of cosmic infancy. We are not the masters of our domain, but rather a young species being monitored, perhaps even graded, on our ability to manage our own planet, overcome our internal conflicts, and mature technologically without self-destructing. It suggests that there is a threshold we must cross, a level of societal and ethical maturity we must achieve before the galactic gates are opened and we are invited to join the wider community of intelligent life. What might that threshold be? It could be the achievement of sustainable global peace, the responsible stewardship of our biosphere, or perhaps the demonstration that we can venture beyond our solar system without being a destructive or aggressive force. Until we meet that standard, we remain in the zoo, allowed to develop in our own enclosure, unaware of the vast civilization just beyond the invisible bars. Of course, the cosmic zoo hypothesis is not without its own set of profound questions and criticisms. For one, it assumes a remarkable degree of unity and discipline among all potential alien civilizations. Is it really plausible that every single advanced society across the entire galaxy would agree to and perfectly adhere to such a non-interference policy? There would always be the risk of a rogue actor, a civilization that breaks the rules and makes contact for its own reasons, whether out of curiosity, malice, or a desire to proselytize. Furthermore, the hypothesis raises the unsettling possibility that we are not just in a zoo, but in a nature preserve. Are we being protected for our own benefit, or are we being cultivated, studied, or even reserved as a resource? The darker interpretations, while speculative, remind us that the motivations of a truly alien intelligence are ultimately unknowable and may not align with our own concepts of benevolence. Despite these uncertainties, the cosmic zoo hypothesis offers a uniquely hopeful and challenging perspective on our future. It reframes the great silence of the cosmos not as a void of loneliness, but as a period of probation, a test of our collective character. It gives us a goal that is far grander than merely finding other life. It challenges us to become the kind of species that is worthy of being found. Every step we take towards solving our global problems, from climate change to nuclear proliferation, every effort we make to understand the universe with humility and curiosity, could be seen as us preparing for our final exam, the day we graduate from being isolated inhabitants of a single planet to becoming citizens of a galactic community. The silence, then, is not a wall but a door, and the key to unlocking it lies not in building a bigger radio telescope, but in building a better version of ourselves. While we scan the galaxy with billion-dollar telescopes and debate the grandest theories of cosmic life, it's humbling to remember that we may have already found the first evidence of it nearly 50 years ago, sitting in the dust just beneath our robotic feet. In the summer of 1976, humanity achieved an incredible milestone. Two robotic laboratories, Viking 1 and Viking 2, made soft landings on the surface of Mars. Their mission was audacious: to perform the first ever in-person experiments designed to detect life on another planet. The most famous and controversial of these was the labeled release experiment, a masterpiece of scientific ingenuity devised by its principal investigator, Gilbert Levin. The design was brilliantly simple and direct. A small sample of Martian soil was scooped up by the lander's robotic arm and deposited into a tiny chamber on board. Then, a nutrient soup rich in carbon-14 labeled organic compounds was injected into the soil. The idea was straightforward. If there were any Martian microbes present, they would presumably eat the food, metabolize it, and then exhale or excrete waste gases, just as terrestrial microbes do. Because the nutrients were labeled with the radioactive carbon-14, any gaseous byproducts of this metabolism like carbon dioxide or methane would also be radioactive. A series of sensitive detectors were poised to sniff the air inside the chamber, listening for the telltale radioactive breath of a living organism. What happened next sent a jolt of excitement through the control rooms on Earth. In both Viking landers, separated by thousands of miles on the Martian surface, the result was the same. A rapid, sharp increase in radioactive gas was detected immediately after the nutrient was added. It was a positive result. The graph spiked exactly as you would predict if Martian microbes were in the soil, eagerly consuming the food that had been delivered to them. Gilbert Levin, convinced of the elegance of his experiment, believed he had found evidence of life on Mars. The data seemed clear, yet this initial thrill was short-lived. The triumph of the labeled release experiment quickly became its burden, because another instrument on the Viking landers, the gas chromatograph mass spectrometer, had performed a different test. It heated the Martian soil and analyzed the vapors, searching for the complex organic molecules that are the very building blocks of life. It found nothing. The soil appeared to be utterly sterile, devoid of any organic material. This negative result created a profound contradiction. How could there be life metabolizing food if there were no organic molecules present to constitute that life in the first place? The scientific consensus faced with this paradox made a difficult choice. It was decided that the labeled release experiment's positive signal must have a non-biological explanation. The exciting prospect of life was set aside in favor of a sterile Mars, and the legacy of Viking was cemented as a noble but ultimately unsuccessful search. For decades, the official story was that the labeled release result was a false positive, a quirk of Martian chemistry. The leading theory proposed that the Martian soil was filled with powerful oxidizing agents like peroxides or superoxides. These harsh chemicals, the thinking went, could have broken down the nutrient solution all on their own, producing the same radioactive gases without any need for biology. It was as if you poured a soft drink onto a pile of bleach and saw it fizz. The reaction looks lively, but it's purely chemical. This explanation became the textbook answer, and the tantalizing possibility raised by Levin's experiment faded into a historical footnote, a cautionary tale about the perils of interstellar false alarms. Yet Gilbert Levin never accepted this conclusion. For the rest of his life, he maintained that his experiment had in fact found life, and that the other instrument's failure to find organics could be explained. He became a vocal and persistent advocate for re-evaluating the Viking data, a voice in the wilderness insisting that the answer had been there all along. The incredible twist in this story is that modern discoveries made by a new generation of Martian rovers have completely upended the context of those 1970s results, vindicating Levin's long-held position in a way he could only have dreamed of. We now know, thanks to the Curiosity and Perseverance rovers, that the Martian soil is not devoid of organic molecules. They have been found in multiple locations, in sediments and in drilled rock samples. The early assumption that the gas chromatograph mass spectrometer's negative result was definitive has been proven wrong. That instrument was simply not sensitive enough. It was like trying to find a single specific grain of sand on an entire beach with a metal detector that wasn't tuned finely enough. We now know the organics are there, which removes the central objection to the labeled release experiment's biological interpretation. If the building blocks of life are present, then the possibility that life itself was there, metabolizing the nutrients, becomes a legitimate and compelling explanation once more. Furthermore, our understanding of Martian chemistry has also evolved. The theory that powerful oxidants like hydrogen peroxide were abundant in the soil and caused the reaction has been challenged. Subsequent missions have found little evidence for the global presence of such chemicals in the concentrations needed to produce the rapid, strong signal that Vikings saw. Other proposed chemical explanations involving minerals like perchlorates also struggle to fully replicate the specific results. The labeled release experiment included a control. After the initial positive reading, the soil was heated to a temperature that would certainly kill any known microbe, and then the nutrient was added again. This time there was no gas release. The life, if it was there, had been sterilized. This control is very difficult for many non-biological theories to explain. A purely chemical oxidant would likely still be present after heating and would continue to react with the nutrient, but it didn't. The signal stopped, just as you would expect if you had killed a living organism. This re-evaluation turns the Viking mission from a closed case into one of history's most profound what-if moments. What if we had interpreted the data differently? What if we had followed up with a mission specifically designed to test the biological hypothesis further? The decades-long gap in Mars lander missions that followed Viking might have been filled with a frantic, focused search for life. Gilbert Levin's unyielding belief forces us to confront an uncomfortable truth about the scientific process. Sometimes a paradigm is so powerful that it can cause us to dismiss anomalous data, even when that data is correct. The paradigm of a dead, sterile Mars was so strong in the 70s that the simpler explanation that the experiment worked and found life was rejected in favor of more complex chemical theories. The story of the labeled release experiment is a cautionary tale about the power of preconceived notions, but it is also a story of stunning vindication. It stands as a powerful reminder that the first evidence for life beyond Earth may not come as a crisp signal from a distant star or a complex analysis from a future rover, but from a simple, elegant experiment from a past generation, whose true significance we are only now, with the benefit of hindsight, truly beginning to appreciate. Now, let's turn our attention from the chemistry of life to one of its most crucial physical protectors, a planet's magnetic field. Think of a magnetosphere as an invisible force field generated by a planet's churning, molten core. This dynamic, swirling ocean of liquid metal acts like a gigantic electrical generator, creating a powerful magnetic bubble that extends far out into space, wrapping the entire world in a protective embrace. Without this shield, a planet is essentially naked, exposed to the full, relentless fury of its star. Our sun, for all its life-giving light, is constantly blasting out a torrent of high-energy particles, a supersonic wind of radiation that streams across the solar system. For a world like Mars, which lost its global magnetic field billions of years ago, this solar wind has been a death sentence. Stripped of its planetary shield, the Martian atmosphere was gradually eroded away, molecule by molecule, blasted into the void by these charged particles. This process transformed Mars from a potentially warm, wet world into the cold, desolate desert we see today. A strong magnetosphere acts as a cosmic deflector shield, bending these dangerous particles away from the planet and safely around it, channeling them toward the poles where they create beautiful auroras rather than atmospheric destruction. But deflecting the solar wind is only part of the story. the magnetosphere's role is even more profound when we consider the long-term preservation of a world's atmosphere and its liquid water. An atmosphere is not just the air we breathe, it's a planetary pressure jacket and a temperature regulator. It provides the surface pressure necessary to keep water in its liquid state, preventing it from instantly boiling away into the vacuum or freezing solid. It also helps distribute heat around the planet, moderating extreme temperature swings. When a planet loses its magnetic shield, it doesn't just lose its air, it begins to lose its very capacity to host liquid water on its surface. The process is slow but inexorable. As the atmosphere thins, the surface pressure drops. Eventually, it falls below what's known as the triple point of water, the specific pressure at which water can exist as a liquid. When that line is crossed, any remaining water on the surface can only exist as ice or vapor, instantly sublimating into the sky. This is the fate that likely befell Mars, and it's a primary reason why a strong, global magnetosphere is now considered a non-negotiable component for sustaining long-term, surface-based life as we know it. This understanding forces a major shift in how we evaluate the thousands of exoplanets we're discovering. For years, the primary criterion for habitability was the habitable zone, that Goldilocks orbital distance where temperatures are just right for liquid water. But we now know that's only the first and most basic filter. A planet can be perfectly positioned in the habitable zone, but if it lacks a magnetic shield, it could be a barren, airless rock, its potential for life stripped away eons ago by its own star. This is especially critical for planets orbiting red dwarf stars, which are the most common stars in our galaxy. Red dwarfs are notoriously tempestuous, especially in their youth, prone to frequent and violent superflares that unleash 100 times more ultraviolet and X-ray radiation than our Sun ever does. A planet in the habitable zone of a red dwarf is already orbiting very close to its star to receive enough warmth. Without a powerful magnetosphere, such a world would be cooked, its atmosphere utterly ravaged by this relentless stellar fury. The presence or absence of a magnetic field could be the deciding factor between a lush, watery world and a scorched, sterile wasteland, even if both are located in the theoretically perfect spot. Detecting whether a distant exoplanet has a magnetosphere is one of the next great challenges in astronomy, but scientists are already devising clever ways to look for this invisible shield. One promising method involves watching for auroral radio emissions. Just as Jupiter's powerful magnetic field generates intense radio waves, an exoplanet with a strong magnetosphere should produce a similar detectable signature. Another technique involves observing how the planet interacts with its star's stellar wind. When a planet with a magnetosphere passes in front of its star, the interaction between its magnetic bubble and the star's particles could create a slight, telltale dimming or a specific signature in the star's light that wouldn't occur with an unprotected world. As our telescopes become more sensitive, searching for these indirect clues will become a standard part of the exoplanet habitability assessment. It moves us beyond simply asking, could water be liquid there? To the much more sophisticated question, could this world actually protect and preserve the conditions for life over billions of years? The magnetosphere, once a footnote in planetary science, has now stepped into the spotlight as a guardian of life, a hidden structure that may make the ultimate difference between a living world and a dead one. This brings us to a powerful moment of synthesis, a chance to gather all the evidence we've explored and plug it into one of the most famous thought experiments in the history of science, the Drake equation. Conceived by astronomer Frank Drake in 1961, this was not a formula designed to produce a single, definitive answer, but rather a structured way to frame the enormous question of how many communicative civilizations might be sharing our galaxy. It breaks down this grand unknown into a series of smaller, more manageable variables. For decades, filling in these variables was an exercise in sheer guesswork, leading to estimates that varied from millions of civilizations to just one, us. But today, we are no longer guessing. We are witnessing a revolution in data, and when we update the Drake equation with our modern discoveries, the results are more compelling and optimistic than they have ever been. Let's walk through the equation step by step, starting with the first few factors that we now have solid numbers for. The equation begins with the rate of star formation in our galaxy. We now know the Milky Way forms new stars at a steady pace, but since we're interested in civilizations that have had time to arise, we're more focused on the total number of stars that have ever formed and are still shining. That number is staggeringly large, in the hundreds of billions. The next factor is the fraction of those stars that have planets. Just a generation ago, this was a total unknown. Today, thanks to missions like Kepler, we know with near certainty that virtually every star has at least one planet. This single update transforms the equation dramatically. We are no longer talking about a galaxy where planets are rare exceptions. We are talking about a cosmos that is richer in worlds than it is in stars. Then comes the number of planets per star that can support life, the habitable zone. This is where our discoveries have truly shattered old paradigms. We used to picture the habitable zone as a narrow, delicate ring. But now we must account for the icy ocean worlds like Europa and Enceladus, which are heated from within by tidal forces, completely redefining the concept of a life zone. We have to include the Hycean worlds with their global oceans beneath hydrogen atmospheres, which can stay warm much farther from their stars. And we cannot forget the potential for life in the cloud decks of gas giants or in the deep, dark subsurface aquifers of Mars. This factor is no longer just about finding an Earth twin. It's about counting all the environments where liquid water and energy can meet. When we add these new classes of habitats to the traditional rocky planets in the Goldilocks zone, the number of potentially life-supporting worlds in our galaxy skyrockets from a conservative few billion to a number that is almost incomprehensibly large. Now we arrive at the most contentious and fascinating part of the equation, the fraction of those habitable planets where life actually appears. This is the great leap, the transition from chemistry to biology. For decades, the rare Earth hypothesis suggested this fraction could be vanishingly small, that the spark of life was a miraculous fluke. But our modern understanding of prebiotic chemistry forcefully argues the opposite. The Miller-Urey experiment and its successors showed us that amino acids form readily under a wide variety of early planet conditions. We've detected these same complex organic molecules in interstellar nebulae and confirmed their delivery to the early Earth via carbonaceous chondrite meteorites. The universe isn't just capable of making the ingredients for life, it is actively and constantly manufacturing them and scattering them everywhere. This suggests that the emergence of life is not a miracle, but a near-inevitable outcome of cosmic chemistry. Given a reasonably stable, energy-rich, watery environment, life seems to be a natural process waiting to happen. This pushes the value of this factor away from a tiny decimal and toward a much more significant number, implying that the galaxy is likely teeming with microbial life. The next step is the fraction of those life-bearing worlds where that life evolves intelligence. This is perhaps the biggest remaining unknown. The incredible tenacity of extremophiles shows us that simple life is incredibly robust, capable of persisting in hellish conditions for billions of years. But does that simple life always, or even often, evolve into complex, tool-using, intelligent beings? This is the core of the debate. On Earth, it took over 3 billion years for single-celled life to make the leap to multicellular organisms. That long delay could imply that this step is the true bottleneck, the real great filter. It might require a very specific and rare set of planetary circumstances, a large stabilizing moon, plate tectonics, a magnetic field, and a remarkable run of good luck avoiding extinction-level asteroid impact. It's entirely possible that while microbial life is a cosmic commonplace, the silence we hear is because intelligent, technological civilizations are the true rarity. islands of consciousness separated by vast gulfs of space and time. Finally, we have the last two factors: the fraction of intelligent civilizations that develop technology that releases detectable signs of their existence, and the length of time such civilizations release those signals into space. This is where our own human experience becomes a sobering data point. We have only been a technologically communicative species for about a century, a mere blink in the cosmic eye. Is our future one of long-term stability, where we learn to manage our planet and our technology for thousands or millions of years? Or is our technological adolescence also a precursor to self-destruction, making the longevity of such civilizations tragically short? The answer to this question dramatically changes the final number. If civilizations typically wipe themselves out quickly, then the galaxy might be full of the silent ruins of short-lived societies. But if even a small percentage learn to survive and thrive for geological timescales, then the galaxy should be buzzing with activity. When you put it all together, the modern Drake equation tells a story of a galaxy that is lush with potential. The early factors, which were once pure speculation, are now supported by hard data pointing toward an abundance of stars, planets, and habitable environments. The middle factors are bolstered by a new understanding of life's chemical inevitability and its incredible resilience. It is only in the final steps concerning intelligence and longevity where the great uncertainties and the great filters likely reside. The updated equation doesn't give us a single number, but it paints a picture that is far from lonely. It suggests that the Milky Way is likely a living galaxy, filled with microbes and maybe even complex organisms on countless worlds. The profound silence we perceive when we listen for radio signals may not be a sign of emptiness, but a testament to the final, formidable challenges of intelligence and time. The equation is no longer a question of if life is out there, but a guide for how we might finally find it, and a reminder that our own long-term survival may be the most important variable of all. The sheer weight of all this evidence, from the chemical whispers in Martian soil to the organic snow falling on Titan, creates an undeniable momentum. We are no longer merely hoping to stumble upon a sign of life. We are now strategically building the machines and missions with the explicit goal of finding it. This is the final frontier of our investigation, moving from gathering clues to conducting a direct interrogation of the cosmos. The next decade will see an unprecedented fleet of robotic explorers and observatories dispatched to the most promising corners of our solar system and beyond, each one a specialized detective equipped to answer the ultimate question. Leading this charge is a mission of profound elegance and ambition, the Europa Clipper. This isn't a spacecraft that will orbit Europa continuously, as the radiation environment around Jupiter is too punishing for such a long-term stay. Instead, it will perform a daring series of nearly 50 close flybys, swooping in to gather data and then retreating to safer ground. Its suite of 9 powerful instruments is a dream team for astrobiology. High-resolution cameras will map nearly the entire surface, searching for fresh signs of geologic activity and those tantalizing plumes. An ice-penetrating radar will act like a cosmic ultrasound, peering through the frozen crust to measure its thickness and hunt for those hidden, shallow lakes of liquid water that might be trapped just beneath the surface. But the most critical instrument might be its mass spectrometer, poised to perform a direct chemical analysis if the Clipper is fortunate enough to fly through one of Europa's erupting geysers. It will taste the ejected particles, looking for the complex organic molecules and salts that would confirm the ocean's habitability. The Europa Clipper's mission is to perform a thorough reconnaissance to tell us if that global ocean is indeed the life-friendly environment we suspect, and to identify the best landing sites for a future mission that might one day drill through the ice and dive into the darkness below. While the Clipper surveys an alien ocean from above, here on Mars we are initiating the most complex robotic campaign ever attempted, the Mars Sample Return. For decades, our rovers have been our remote geologists, but they are limited by the size and complexity of the instruments they can carry to another world. The Perseverance rover is the first critical step in a grander plan, acting as a mobile, intelligent sample collector. It has been meticulously scouring the floor of Jezero crater, an ancient river delta, drilling out core samples of the most scientifically promising rocks and sediments. These aren't just random souvenirs, they are carefully selected chapters from Mars's geological history, sealed in ultra-clean tubes and cached on the surface. The next phase of this interplanetary relay race involves sending a new lander to Mars, which will carry a small fetch rover to retrieve these tubes and load them into a sophisticated ascent vehicle. This rocket will then launch from the surface of Mars, a historic first, and place the precious cargo into Martian orbit. There, a waiting European spacecraft will capture this basketball-sized container and begin the long journey back to Earth, ultimately releasing a capsule to parachute the samples safely into a secure laboratory facility. The scientific value of having pristine Martian rocks in our best labs here on Earth cannot be overstated. Scientists will be able to analyze them with instruments far more powerful and delicate than anything we can send on a rover. They will search for subtle chemical patterns, microscopic structures, and isotopic signatures that are the unambiguous fingerprints of past life. This is the kind of forensic evidence that could settle the debate over the Viking results once and for all. Finding a fossilized microbial community or a complex organic molecule with a distinctly biological origin in a Martian rock would be the moment everything changes. It would prove that life is not a unique property of Earth, and it would open up the entire solar system as a potential abode for biology. Venturing further out to the hazy, orange skies of Saturn's moon Titan, we have a mission that feels like it was pulled from the pages of a science fiction novel. Dragonfly is not a rover, it's a nuclear-powered dual quadcopter drone, an aerial explorer designed to capitalize on Titan's thick atmosphere and low gravity, which make flight remarkably efficient. This flying laboratory will be able to traverse dozens of miles between landings, hopping from one site of astrobiological interest to another in a way no wheeled vehicle ever could. Its primary target is Selk Crater, a location where scientists believe liquid water once mixed temporarily with Titan's complex organic material. Dragonfly will land on the moon's dune fields, which are covered in that dark, organic sand that has been snowing from the sky for eons. Its onboard instruments will then perform on-the-ground chemistry, literally tasting the surface to identify the specific probiotic molecules present. The mission will search for the building blocks of life, like amino acids and nucleobases, and it will investigate whether the chemistry has advanced toward the formation of membrane-like structures that could enclose a cell. By exploring Titan, we are essentially traveling back in time to witness the chemical steps that may have led to life on Earth, all while learning if an entirely different biochemistry, based on liquid methane instead of water, could be possible. Finally, our search extends far beyond our solar system, powered by a new generation of colossal ground-based telescopes that will push the boundaries of what we can see. The Extremely Large Telescope, or ELT, currently under construction in Chile, will have a primary mirror an astounding 39 meters across. This colossal eye on the sky will gather 15 times more light than the largest optical telescopes operating today. Its primary goal in the search for life will be to directly image and analyze Earth-sized exoplanets. It will be powerful enough to separate the faint light of a small, rocky world from the overwhelming glare of its host star. Once it has a planet in its sights, its sophisticated spectrographs will break down that light, searching for the telltale biosignatures in its atmosphere. The ELT won't just be looking for the generic presence of gases. It will be searching for the specific, dynamic combinations that scream life, like the persistent coexistence of oxygen and methane. It might even be able to detect the red edge of chlorophyll, the signature of widespread vegetation on a continent, or the artificial glow of city lights on the planet's dark side. These telescopes represent the culmination of centuries of astronomical advancement, giving us the power not just to find other worlds, but to study them in exquisite detail, to read their atmospheric stories, and to finally know if the pale blue dots we find are also like our own living dots. Together, this armada of explorers and observers forms a coordinated, multi-front assault on one of humanity's oldest mysteries. We are sending a submarine's eye to an ocean world, a robotic archaeologist to gather the rocks of Mars, a flying chemist to a prebiotic laboratory, and building giant eyes to scan the atmospheres of distant Earth. Each mission is a specialized tool designed to probe a different facet of the same profound question. The evidence we have gathered so far is no longer just a collection of intriguing clues. It is a roadmap pointing us directly toward the most promising places to look. The next chapter in this great cosmic detective story is about to begin, and for the first time, we are not just the ones asking the question. We are the ones who are poised to find the answer. And so, our journey through the cosmos brings us to a moment of profound reflection. We have ventured from the acidic clouds of Venus to the hidden ocean of Enceladus, from the mysterious methane pulses on Mars to the fleeting brilliance of the WOW signal. We have explored the possibility of floating life in the skies of gas giants, contemplated the silent watch of a cosmic zoo, and even revisited the tantalizing possibility that we may have already found life on Mars nearly 50 years ago. Each of these 30 discoveries is a piece of a grand, interconnected puzzle, a clue in the greatest detective story ever told. Individually, they are fascinating scientific breakthroughs. But together, they form a crescendo of evidence, a powerful and consistent narrative pointing toward one incredible conclusion. The universe is not a sterile, empty void. It is a vibrant, creative, and chemical-rich arena, seemingly custom-built for life to emerge. We have not yet held that definitive proof in our hands, but the trail of clues is now so abundant, so compelling, that it feels less like a question of if we will find life, and more a question of when we will finally connect the final dots. This changes our place in the cosmos. For millennia, we gazed at the stars from a position of assumed solitude, wondering if we were a singular, miraculous accident. Today, that perspective is shifting. The evidence suggests we are not a fluke, but perhaps a part of a cosmic norm. The same physics and chemistry that forged stars and planets also forged the amino acids in the Murchison meteorite and the complex organics in Titan's haze. The same processes that power the sun also drive the hydrothermal vents on Earth's ocean floor, which may have their mirrored counterparts on the seafloors of Europa and Enceladus. Life appears to be a natural and perhaps even an inevitable outcome of a universe that is hardwired for complexity. We are not separate from the cosmos. We are a conscious expression of it, a way for the universe to look back upon itself and ask these very questions. This realization is both humbling and empowering. It tells us that we belong to a much larger living family, even if we have not yet met our relatives. Therefore, this is not an end, but a spectacular beginning. The mission's now underway, or on the drawing board, Europa Clipper tasting the plumes of an alien ocean, Dragonfly flying through the hydrocarbon skies of Titan, the Mars Sample Return Campaign seeking to bring a piece of the red planet home, and the next generation of telescopes that will read the atmospheres of distant Earths. These are the instruments of our next great leap. The answer is no longer a distant dream. It is a tangible goal within our scientific lifetime. The great silence of the cosmos is not an emptiness. It is the quiet before a revelation. It is the space in which we are patiently, meticulously building the case that will forever change our story. So the next time you find yourself under a clear night sky, look up. Let your gaze travel past the familiar constellations and into the deep black between the stars. See it not as a void, but as a canvas of infinite possibility. See the pinprick of light that is Jupiter and imagine the potential biosphere floating in its clouds. See the faint glow of the Milky Way and picture the countless Hycean worlds with their global oceans and the rocky planets in their habitable zones where life may have taken root billions of years before our own. You are living in the generation that stands on the precipice of knowing. Your curiosity, your support for science, and your sense of wonder are all part of this grand endeavor. Stay curious because the next headline, the next breakthrough, the next image from a distant world could be the one. The evidence is all around us, whispering on the solar wind, encoded in the light of other suns, and waiting in the ice of alien moons. The greatest discovery in human history is out there, and it is closer than it has